Hey guys, welcome to 118C synth guide for midterm 1. And for those of you guys who have seen these before, or if you haven't, just a reminder of what this is. Purpose of the video is just to go through the significant transformations for midterm 1 of 118C. Kind of train your eye to see the patterns, right? Train your eye to see how you can make certain groups, what to think about in the synthesis and whatnot. And also, for those of you, again, who might remember, don't remember, I like to also use a synth guide to kind of teach my favorite approach to synthesis, which is retrosynthesis, to show you that even if you're completely stuck, you can at least, work in a non-traditional way in your synthesis to help figure out what are some acceptable intermediates that could have existed. Okay. So in the past, I've kind of always just done all of the relevant transformations all at once and kind of taught little tricks here and there. But I think just for the sake of clarity and the little sake of, for a little bit of sake of organization, I'm going to break this video up into parts. The first part is just going to go over how to make the transformations of carboxylic acids, how to make carboxylic acids. What are the transformations that do that? So we'll see how many different ways you can get to the carboxylic acid, because at the end of the video, I'm going to make the argument that really the hardest thing to do in any 118C midterm 1 synth is to make the carboxylic acid in the first place. Making the derivative is easy. It's making the acid in the first place that's hard. So we'll look first at how we can make acids from many different things. Then we'll look at derivative chemistry, and then we'll do a bunch of practice problems so that we can really hone in all these components together. And you guys get to see me do synthesis problems and see how you can apply my thinking, or use my thinking in your thinking as well. Cool. So without further ado, let's just get right into it. So again, midterm 1, chapter 1920. Chapter 19 is all about the carboxylic acid. So we should kind of remind ourselves on how we make carboxylic acids in the first place. Like I mentioned in the content lecture, all throughout 118A, we learned different ways to make the carboxylic acid. So if you think, in terms of like a 118A synthesis, right? The very first reaction we ever learned in 118A right, in this class was the Br2HV, or the radical halogenation of an alkane chain. And so we can radically halogenate an alkane like that to get a bromine as such. This bromine we could then substitute in an SN2 fashion with a hydroxide. And what we'll get is this alcohol here. Now, this primary alcohol is very important because primary alcohols have 2 hydrogens, right, located on that alpha carbon. And those 2 hydrogens can be oxidized in a Jones oxidation to give a carboxylic acid. So one of the very first ways we learned to make acids in all of OChem was the Jones reaction. As long as we had a primary alcohol and we had, access to Jones, which we will have, right, as a synthetic tool, you could make carboxylic acids. So the question becomes, how many different ways can we make primary alcohols? Well, if we keep the simplicity of 118A, right, one way to make it was to, start from a 2-carbon chain to end with a 2-carbon chain. So this is the same number of carbons. We just had to employ a simple SN2. Okay, so same number of carbons, right? We employ a simple SN2. We could also take a slightly different route here and use Mg ether to make the Grignard reagent. And the Grignard reagent, which is a carb anion, could be used to attack certain electrophiles to help us access, again, that primary alcohol. One of those is a formaldehyde. And that gives us the primary alcohol. However, it doesn't just simply give us a primary alcohol of the same nature as the one we just made. We get a primary alcohol that is 1 carbon longer. So again, same number of carbons, right, throughout the first synthesis, but this synthesis adds in an extra carbon, right? So we add in that extra carbon from the formaldehyde. Again, primary alcohol. So once we get Jones, we can make the carboxylic acid. Okay, so if we want to add a carbon, we could use this synth. But there is actually a synth that we learned in 118C that kind of makes this one a little bit obsolete. not as good. So we will see that one, but it's basically using the same idea as the Grignard synth here. We could also just open an epoxide. And this really only works with non-substituted epoxides, and I'll explain why in a second. But we could do this. Get this alcohol. And then again, Jones gives us the carboxylic acid. So once again, if we think about the number of carbons, it's always 2. It's 2 here and 2 here. But notice how the epoxide adds in these extra 2 carbons here. So an elongation of the chain by 2 carbons, or adding 2 carbons, basically gives us, or that's what's given to us by the epoxide synthesis. Okay. So really with 118A, it was all about, hey, make primary alcohols and then oxidize them, right? As long as we have a primary alcohol, we can just oxidize it with Jones. And that was our route to the carboxylic acid. All right. And so again, this synthesis here has a better way. We have a better way to do it in 118C. 118C way better. Okay, but the epoxide synthesis is going to basically stick around, and you can use it in the class if you'd like. Now, I mentioned that this has to be unsubstituted, and the reason is because if we did this synthesis here, where one side is substituted, let's use that same Grignard, what we're going to get is not what we want, because the Grignard, if it attacks less or more sub, we can completely control for that, in the sense that Grignard always attacks the less sub. But if it always attacks the less sub, then that means that we're always going to get a secondary alcohol. There's no way to get a primary alcohol out of this reaction, and therefore this reaction is not very good for making carboxylic acids, because even if I use Jones here, all I'm going to get is the ketone. We're going to just get the ketone here, and that's not very good for our synthesis, right? We want to make carboxylic acids. Okay, so just things to think about on that. So when we entered 118B, right, with only the knowledge that we need primary alcohols to make carboxylic acids, we started the unit off with alkenes. And so how can we make a primary alcohol from this alkene? Well, we can actually just hydrate alkenes. So we can hydrate them to either make this alcohol or we can make this alcohol, known as the Markovnikov and the anti-Markovnikov, respectively. Again, we want a primary one right now. So for the time being, primary is what we want. So we would go with the anti-Mark hydration. Just a reminder, that's just BH3 THF. And the second step typically being peroxide in base. Okay, and that would give us the anti-Mark alcohol. Now, again, now that we have this reagent, we can just do Jones, and what we get is the carboxylic acid, as we intended to have. Okay, once again, we start with 3 carbons, and we end with 3 carbons. So this is a great way to get the same number of carbons. Now, we could also take the alkene and turn it into a bromide, because remember back here we also used the Grignard synth. So we could either do a primary alcohol like from the bromide, or we could do the Grignard to the alcohol, and so we could also add a bromine. Now keep in mind we want the primary bromine, not the secondary bromine, right? Secondary bromine is what we would get if we just did HBr, right? The Markovnikov bromine. To get the anti-Mark bromine, we have to do the peroxide synthesis. And remember, only bromine can do the peroxide synthesis. No other halogen can do it. So we really do need to make sure we use bromine here. But once we get to here, we can do the Grignard synth again. And we could do either one of the two, right? Although remember, the formaldehyde synthesis is a little bit obsolete, so I'm not going to include it this time. But something to just keep in mind. I guess you could do it if you wanted to, but again, we're going to learn a way better one that doesn't require us to go through the formaldehyde. Once again, we can add 2 carbons here to the chain. with an epoxide. And we can just do a Jones oxidation, and that gives us the carboxylic acid. Okay, we get a carboxylic acid here. Alkenes are interesting, right? Because, you know, with the alkane, we had to go through the bromide to get to the oxygen here, but we can do directly, you know, oxygenate. We don't have to really worry about going through a bromide. We could go through a bromide if we wanted to do an elongation, right? An elongation, we could do that. It's totally possible. But this is just a reminder of how these reagents work. Alkynes were kind of similar, right? In that, hey, if I were to add one HBr, right, in ROR, so I'm specifically trying to control here this reaction, one equivalent HBr with a peroxide, I could make the vinyl halide. Now, vinyl halides are interesting because you can't substitute vinyl halides, right? You can't really substitute them. So all we could really do here is a metallation, or, you know, turn this into a Grignard. And suddenly we have a vinyl Grignard that, when reacted with, like, let's say an epoxide, gives us this interesting relationship here. Okay, so we get this interesting relationship here, where we sort of retain that double bond that didn't exist before, right? Here, the double bond completely goes away, but here we keep one, or we keep a pi bond. And so we get an interesting reaction where we have a complete retention of one pi bond. That's not that it's hard to do, but it's, you know, if you try to do it like the regular way, it'd be really hard to do that. Like if you try to do it from an alkene or something, is what I'm trying to say. Okay, so this is interesting in that we get a vinyl Grignard, okay, or like a vinyl reagent, right, which is not something common. We're also going to see this again, this vinyl pop up, and see how, like, noticing that there is a vinyl, you know, reagent in your reaction kind of tells you which synth to go towards. Okay, we can also, from the same alkyne, do a asymmetric hydration. Or asymmetric would be the wrong term there, actually. We can do an anti-mark, is what I should say. Do an anti-mark hydration. And what we get initially is an enol that quickly tautomerizes into the aldehyde. Okay, so the boration enol turns into an aldehyde, and that guy, we know we can just use Jones and turn into a carboxylic acid. This synthesis is kind of basically the same as this guy here in that it keeps the same number of carbons. I guess I can just, I don't need to use, I think I can just use this colors. I've already written on the side what those colors mean anyway. So we kind of retain these three carbons. So 118B, initially we learned these sort of syntheses, or we were able to add these syntheses to our, you know, synthetic toolkit of how to make carboxylic acids. Okay, once again, going towards that either primary alcohol, you know, that we can get, or are we going towards, like, you know, an enol that can tautomerize into a carbonyl and then oxidation of that carbonyl. Now 118B didn't really stop there, because right at the end there of 118C, we learned a couple more reactions that we could do. A couple of them are a little bit oddball. And when I say oddball, what I mean is, like, they're a little bit different, a little bit weird. For example, this reaction here that we also learned in 118C, right? If we were to react this with CamNO4, OH minus H2O, right, and heat, we can essentially destroy any position here that has a benzylic hydrogen. So what do I mean by destroy? As long as that dark blue hydrogen exists, this whole component is replaced by a carboxylic acid. Okay, H plus H2O. Okay. This part here, benzoic hydrogen, completely replaced by a benzoic acid. But this guy here with no benzoic proton kind of just stays the same. Okay, so the benzoic proton is particularly important here. Again, this is also something we learned in 118C as well. So if we ever need to make a benzoic acid, so benzoic acids, the way to do it is with KMNO4. Okay, so anytime you see benzene, you want to think KMNO4, right? This is our access to the benzoic acids. Cool. Another sort of oddball reaction that we learned is the MCPBA reaction, right? So we learned that, hey, if we have an aldehyde here, we can use MCPBA, normally an epoxidating agent. You can use MCPBA to react on the aldehyde H side. Okay. If we use the ketone, we'll see this is going to be more important for, this is a little more important for the derivative chemistry, but MCPBA can also react with ketones. What it does is it gives us esters. Okay, so normally it would give us an ester, and an ester on the more substituted side. So we call this migratory aptitude, but the likelihood that the oxygen shows up on a certain side is going to be controlled by H321, right? Like who is more likely to. So aside from hydrogen, right, 321, that's sort of like substitution rules, right? Like carbocation rules. So that's a way to remember it. Increasing substitution is higher likelihood, unless you're a hydrogen. So even if this were tertiary, we were just making tert-butyl acid if we were to do this reaction here. Okay. Now, there is one more reaction that we can do, and it kind of allows us to play a little bit more with these alkenes a little bit. But we can actually do the haloform reaction with methyl ketones. So what does it mean to be a methyl ketone? Methyl ketone means that one side of the ketone can be really anything, right? The other side just has to be CH3. So this part is the important part, is that there is a CH3. If this part doesn't exist, it's not going to work. Okay, but a methyl ketone in basic solution, okay, will give us a carboxylate that can be protonated to the carboxylic acid. Okay, so this is incredible significance, significant reaction. It allows us to oxidize the normally elusive methyl ketone, right? Normally we think ketones are unoxidizable, right? Like we think that you can't go past a ketone. Well, turns out as long as it's a methyl ketone, we can, and we can make carboxylic acids from them. Now, one thing I want you guys to note here is that if we start off with 3 carbons, we start off with 3 carbons, we end off with now 2 carbons. Okay, so this is actually, there's a different color here. This is a loss of 1 carbon. So not very many reactions can do this where we just lose a whole carbon, but this is one of them. So imagine you're doing your carboxylic acid synthesis and you lose an entire carbon, right? That loss of a carbon most likely is the result of the haloform. Now there's another reaction similar to this, not very often talked about, which is why I didn't mention it too much. But we could take an alkene and do an ozonolysis. But instead of doing the reductive environment we're used to, which is H2S, that's a typical one, or we see zinc, these are known as reductive environments, we can specifically use a oxidizing environment, H2O2, so that when we perform our cut here, actually, let's do it this way. Any ketone side, again, it's going to stay ketone, but aldehyde sides are going to become carboxylic acids. So this is also another way to lose carbons if you had to lose carbons, right? Here we start off with what, 1, 2, 3, 4, 5 carbons. We end off with only 2 carbons in our acid. So this is another way to lose carbons if we had to. Okay. But considering that you guys didn't explicitly learn this reactions, you know, I wouldn't bank on this one being your first top pick. Okay. But to come back to this, right, I mentioned, hey, now that we know the haloform, we can get a little more interesting. The way that we can get a little more interesting is that if we can make a ketone, right, from an carbonyl, or sorry, from an alkene, which we can now access the haloform to get the, or we can now access the carboxylic acid via the haloform. So just to show a quick example of that, right, we can do a hydration here. So that would be Hg. So mercuric acetate followed up by reduction will give us the Markovnikov alcohol, which we can then oxidize using PCC, right? Just keep in mind, right, as long as it's a methyl ketone, so we have a methyl end there, we can do X2, NaOH, and we get the carboxylic acid. Okay, we get the carboxylic acid. So any way you can make a ketone will work now. This guy can also make a ketone. I won't draw the whole transformation, but you can imagine it's going to be very similar to this, just the ketone formation we have to figure out. But HgAOC, or sorry, not HgAOC, it's going to be HgSO4, H2O, right? This will give us the ketone. As long as it's methyl, we can further oxidize it. Okay, so methyl ketone brings in a new level of play on the field, right? And very commonly, people always, this is the question that gets asked that people mess up because they're like, oh, she must, Dr. Stary must have made a mistake because there is a missing methyl or there's a missing carbon, and there's no way that this acid went to this carbon. It's like, oh no, it did. It definitely did. Okay, cool. Now we can do very crazy syntheses just with this knowledge. Okay, but this is just to get you guys' ideas thinking of as to what do I want to aim for, right, to get to my acid, right? There's so many different starting points, right? I can't do every single starting point, but this is sort of to get the blood flowing in your brain as to, okay, this is what I want to do to make these kinds of acids, or if I had a starting material, what are the different ways I can access the acid? Okay, these are a couple of the ways. Now, I guess there's actually one more 118B way before we move on. So there's one more thing we could do. And it will require us to at least have a butanone or a propanol. So butanone and propanol could work here. But this synthesis is sort of like the complement to the haloform because we do acid halogenation, which selectively goes. So if base halogenation goes on the methyl side, acid halogenation selectively goes on the more sub side. And if we use a weak base, like, Na, this is like bicarbonate essentially, we can essentially do an E2 reaction to get to this guy here, which is the enone. Actually, oh yeah, this is, yeah, sorry, this is like an E2. I was thinking of just making, you guys should remember there is ways to just make the enone, like other ways to do it. And those ways can also be used to make the enone. This is just one way. But we can add NaCN here, HCl, which adds a nitrile or a CN on that farthest away alkene carbon or the beta carbon. And beta carbon can be hydrolyzed, as we learned in the content lecture, into a carboxylic acid. So really the pattern here, if there is to be one, right? It's not about adding carbons or losing carbons or anything. The pattern here is that if I were to draw this out, so it looks like this. This here is a alpha, beta, gamma. This is a gamma, or I guess actually it would be the other way around. But just in terms of the ketone, because technically this guy gets naming priority, which unfortunately now you guys need to know how to name things. But anyways, as long as there is a gamma relationship between the ketone and the acid, right, or a 1, 2, 3, 4 relationship between the ketone and the acid, this is your signal that we probably went through the enone. Okay, we probably went through the enone. Where the alpha and beta carbons, right, were part of the enone in the past. And then the acid was added originally as a nitrile, okay? And with the nitrile, this is a great segue into 118C syntheses of carboxylic acids, where things get a little bit interesting. We can actually even start off with the nitrile synthesis because nitriles are technically 118C. But how can we, add nitrile? So we just learned, okay, we can add a nitrile to an enone. That works. So this works. And then we can just hydrolyze. Now, there's two ways you could do this, right? You could do the way that I'm showing now, which is H3O plus and heat. That works. You could also do a base step first. Nothing stopping you from doing that. You can do a basic hydrolysis and then follow it up with acid. It doesn't really matter on paper how you do it. It would matter in real life though, because sometimes acid or base can really affect your molecule. So you might want to choose one over the other. But for you guys, paper chemistry, do whatever the hell you want, right? It's not going to matter. Nitriles are also pretty good nucleophiles. So if I took a bromine and I added NaCN and DMSO, I would get the SN2. Okay, I would get an SN2 reaction. And then the nitrile could then just be hydrolyzed. And so again, if we sort of assess what's going on here, we start with 3 carbons, and then we end with 4. So nitrile adds a carbon. I don't think I've done an add 1 carbon color yet, have I? I don't think so. I have actually. It was green. Okay. Oh, but this color scheme looks really nice though, actually. I'm going to keep it. It reminds me of bubble gum. So we're going to keep this. So we can add a carbon with the nitrile. Okay. Again, SN2 reaction here. So it's a little bit of 118A with a bit of 118C spice in there. But interestingly enough, this is not the only way we can add 1 carbon to make a carboxylic acid. Remember how I said we're going to learn a reaction for 118C that makes that 118A reaction obsolete, right? Well, it's going to require the Grignard. And if to Grignard, so originally we added formaldehyde, right? And that gave us an alcohol. So if we think about this conceptually, to get this immediately to the carboxylic acid, we just have to add this part here, right? Like we just need a carbonyl there, right? So if we just added another carbonyl to the formaldehyde, or we used CO2, then we should be able to accomplish formaldehyde and PCC, formaldehyde and Jones in 1 step. And that's what's going to happen here. We can accomplish this whole reaction just by using CO2 instead. So this is the better reaction. This is better. And just a little bit of lab experience. I've actually used Jones PCC. That stuff really sucks. I'm not sure if it's just specific to what I'm working on, but I really hate using it. It gets really tarry and really sticky. Not very fun in the lab. Okay, but this is what we would expect. Okay. So a very good question arises in that, okay, we have 2 syntheses that do the same thing. So what do we do? Right, if you have 2 syntheses that do the same thing, which one do we choose? And so what I like to do is I like to split this up into a bit of like a couple of criteria that you can think about that can, for the most part, get you to most of the answers. Okay, so for example, we can look at substitution, we can look at hybridization, and then we can look at, this one's an interesting one, you might not have seen this one coming, but we can look at basicity. Okay, so I would do it in this order, but you're welcome to just jump around if you want to. So remember that nitrile is an SN2 reaction. So the substitution of the carbon is going to matter for an SN2, right? For example, if we have a methyl, primary, secondary, or tertiary, right? SN2 reactions work really well, methyl and primary. They can work okay on secondary, so we can make it work, but tertiary is completely inaccessible. So imagine if you had a tertiary carbon, right, versus a primary carbon. So let's say we had this bromine versus this bromine, right? If I had to do the 1 carbon add synth, right, I would probably, And let's say it started like this from this guy here, right? If I had this guy or this guy, I would want to probably do nitrile here and Grignard here. I wouldn't really want to switch, Grignard could work on both of them, honestly, because it's a metallation. Metallations don't really care about substitution, but nitrile will care. So this will work for all of them. I guess what you could say is that, it's very safe to use Grignard if we pass the substitution step. Right? But if nitrile passes substitution step, you should look at the next thing, which is going to be hybridization. Okay. Hybridization is essentially if it's sp3, sp2, or sp. And once again, an SN2 attack really does care about what center we use. For example, sp3, that's where we first learned about SN2, and that'll work. But sp2 and sp are not going to work whatsoever. So if we were to have the same bromine example, let's say this bromine and this bromine, but this guy instead was a vinyl bromide, right? Well, nitrile will work great here, and so will Grignard, but only Grignard will work here. This is kind of what I was mentioning back here, right? Like this vinyl reagent, which we can make from alkynes, can only really be used in the Grignard synthesis, right? And so we can use this Grignard to open up epoxides for the 2-carbon addition, or we can do the 1-carbon addition, right? So this guy, if we did 1-carbon addition, would just look like this. We can actually make conjugated acids, right? So this is a conjugated ketone, this is a conjugated acid. We can make a conjugated acid from this type of reaction here, okay? Now, the very last thing is actually really important, because at this point you might be thinking, well, Grignard really doesn't fail, right? Grignard doesn't fail whatsoever. So why is it that I would ever want to not use the Grignard synth? Well, here's the thing. We need to consider at the end basicity, because nitriles are weak bases, right? They are weak bases, and Grignards are strong bases. So if we had, for example, an NH or an OH or an SH bond on my molecule, Grignard is going to fail miserably, because Grignard will rather do the acid base. Okay, Grignard would want to destroy that acid base proton before it even acts as a nucleophile. On the other hand, nitrile being weak doesn't really care about that proton and has, less of an issue. So a good way to think about this one is, for example, let's say I had an OH here, or I had an OH here, right? Let's say I had an OH here and no OH, right? Grignard synth, so making the MgBr like this, would completely demolish this protein or this proton, right? It's going to grab that proton immediately, and you're going to destroy your reagent, because now it's going to turn into this. It's going to turn into alkoxide, which is not what you want at all. So doing Grignard on an alcohol, or on a molecule with alcohol or an amine or a thiol, is not going to be very good. Nitrile is going to be your intended synthesis. This guy can be either Grignard or nitrile, but the point being that if I had to give one of these guys a choice, I would rather have Mg here and nitrile here. Okay, so Grignard's not always the best, right? Grignard does have some issues sometimes, and it's something that we want to consider moving forward. The only other thing that you should consider, right? So remember that Grignard doesn't only react with CO2, is imagine if instead of an alcohol, we had like a carbonyl like this, right? And we had to turn this guy into this here, right? This is another instance where, let's say we did MgBr here, MgBr is going to instantly attack the carbonyl. Even though it makes a 4-membered ring, it's still going to do it. That's how reactive it is, right? If you just do the nitrile synthesis, which turns this into CN, you don't have to worry about that anymore, that it would do that. Okay, so things to keep in mind, right? Just like ideas to have flowing in your head when you're doing these reactions. Cool. So these are the ways to make carboxylic acids. And again, you can see, like it took 4 pages and almost, like 30 minutes to get through this, right? There is quite a bit of material, right, for making carboxylic acids. So this is really going to be the hard part on your exam, is making the acid. But the easy part is that once I make the acid, making the derivatives is pretty easy. So I'm going to do something I've never done before. I'm going to make you guys a reaction tree or reaction starburst. Just to very quickly highlight how do we transform between derivatives. I'm not going to do too much explaining here. I just want to get this down so that when we go to the really what should be the bulk of this video, which is doing all of the practice problems, we can go back here and see, which functional groups can be made from which derivatives, how can I make different derivatives and whatnot and all that. Okay. So one of the very first reactions we learned was that, hey, SOCl2, right? Or PBr3 works here too, right? Pick your poison, doesn't really matter. But what we can do here is make acyl halides, right? So SOCl2 makes acyl halides from carboxylic acids. And acyl halides, remember, were the most reactive derivative. So we have access to the most reactive derivative right off the bat from the carboxylic acid. So you can always transform into that. We could also make anhydrides, right? But it would have to be 2 equivalents of the same acid. So we'd need 2 equivalents of this guy, and we would have to heat it up, right? We would have to heat it up. And what we would get is, the symmetrical anhydride. Remember, this reaction here, I would never do it. So I'm going to put this here. You could try to do the asymmetric, but remember that this is going to afford you like so many products, right? You're going to get the 2 symmetricals, right? Because you don't know which ones are going to add together. And you're going to get the one mix, right? Very, very bad. So I'm putting an X through it as in you don't want to do that. You want to use something else. AKA, if you really want to get the mix, what you're really going to do is this here. Okay, this is really what you want to do to get the mix. If we want to make an ester, we can do it. It's a bit of an equilibrating reaction, but we can do it with H plus ROH. Okay, and keep in mind that this reaction typically requires about 3 equivalents of alcohol to get it to really work. So it's not always the best reaction, but we can make esters if we had to. And then finally, to make an amide, again, would never do this. It's not very good. You can heat up amine and carboxylic acid. Initially, you'll make the salt, right? The carboxylate salt. Let me make this a little more clear that this is plus and minus. And eventually down the line, maybe a couple days later, it will eventually form the amide. Okay. Again, better way to do this is just to use the acyl halide and amine, excess of it, and you'll get what you want, right? This is way better reaction. So I would probably never do this. Okay. So these are, the ways that you would make derivatives from the carboxylic acid. We can also reduce the carboxylic acid. Lithium aluminum hydride will do it. Really is the only thing that'll touch an acid, to be honest. But with its 4 equivalents of hydride, we use one of them to deprotonate, and then we use the other to completely reduce that carbonyl, right? Or that carboxylate. So we will get the alcohol here. Now, remember, there was 2 other derivatives we learned about of of lithium aluminum hydride. So Dibble and Litba. And the thing is, it doesn't really matter which one you use here, but keep in mind that these guys only have 1 hydrogen. So if I only have 1 hydrogen of Dibble or Litba, so again, it's either one of the 2, not both of them, just either one of the 2, 1 equivalent, all I'm going to get is a deprotonation. So it's not a very good reaction to do. You're not going to get to the aldehyde, that's for sure. So you'll never be able to get to the aldehyde. You would essentially need to drown your carboxylic acid in Dibble. Okay, not gonna really work. Okay, I know that in Leaven's class, so Leaven's class you can do this. So in Leaven's you can, but that's just because you guys cover, I believe, a different mechanism for this class. So Leaven's can do it, but not Nasseri. Nasseri's class can't do this. Okay. In terms of the Grignard, same idea. So if I'd use also like 1EQ RMGBR or RLI. I know that RMGBR is a little too, I've read that it's not strong enough to completely destroy. So I'm not really sure about the excess ideas here, but in terms of 1EQ, not really going to touch the carboxylate. You're going to kind of stop here. So these are the reactions to be aware of the carboxylic acid, right? And again, not going to do too much commentary on these. I just want to just go through these to get all through all the derivatives, you know. Oh, one last thing that's worth mentioning is that the amide here that I incorrectly drew, the amide, if it's primary, right, SOCl2 will give us the nitrile, which is the access to the last part, you know, the last family member. All right, access to the last family member. Cool. So let's just get into now the acyl halide and when transformations can take place here. And keep in mind that acyl halide and anhydride have the same reactions. So we can just talk about them on the same page. We don't really need to separate them. But just keep in mind that in the same way that we can make these guys from acids, we can turn these guys back into acids with water. And so if water works, try organic water. Both of these will give you an ester. Keep in mind for the acyl halide, we're going to want to use pyridine, right? So this here, I'm specifically writing for the, you know, the acyl halide. If we were to use an amine, right? Again, an excess in this case for the acyl halide, what we will get is the amide. And just a reminder that we can make primary, secondary, and tertiary amides depending on the amine that we use. So if we have ammonia, primary or secondary, that's what we would get. We are never really going to be making tertiary amides. That wouldn't really make sense. You might remember I drew that thing. I showed you guys with T, right? We make that weird squid. That's not very happy, right? These are all sad faces. Or angry faces. You can think of these are either eyebrows or it's a frown. It's up to you what you want to choose there, but we don't want to do that. Okay. So acid, alcohol, and amine. Just keep in mind that this guy can turn into this guy if we just introduce carboxylic acid. Okay, carboxylate will work too. So this is actually a really good thing to talk about because I didn't really mention it before, but there's nothing stopping us from using OH minus or H plus here. There's nothing stopping us from using RO minus, and there's nothing really stopping us from using carboxylate. But the point is that if we can do the reaction with the weaker component, right? So the weaker component always being the uncharged species, then just do it with the uncharged species. You know, you want the safer reaction anyways, right? I imagine the charged species will react really fast, pretty exothermic. Maybe if there's a time difference, I wouldn't know about that. I would have to look into it. But you can definitely use the charged species. But I would argue just use the neutral. Just use the neutral if it works, right? If it works, just use that. That actually reminds me, there's one more reaction here. One more thing we can put here that would just make the carboxylate. RO minus, right? RO minus ROH. This is like the base version of the Fischer esterification that we see down here. The base version won't work, right? Because what we need is acid to make sure that the proton on the OH stays in place. Okay, so just a little bit of a reminder on that. Cool. Okay. So these are the derivative reactions. Again, the acyl halide has this extra one here. We could also, what can we also do here? Oh, we can do reductions. So again, lithium aluminum hydride will work here and it will completely reduce both of these into the primary alcohol. NaBH4 will actually also work. So remember that the acyl halide and anhydride are the super reactive derivatives. And I know that I didn't mention too much about NaBH4, but it is something worth considering if we ever need to do a chemoselective reaction. And you'll see what I mean by that when we look at the syntheses. Okay, but NaBH4, the weaker version, will also react with acyl halides and anhydrides. I guess I can give a little example on the side here, right? For example, let's say I had a chlorine here and I had an ester. We're going to learn in just a second that lithium aluminum hydride will destroy both of these guys. So we'll make a diol here. Okay. But if I did NaBH4, right, only the acyl halide reacts. And so now I have a very selective reaction. Here's a little bonus tip. What do you think will happen if I do H+? Okay. So try that out. I won't answer this, but you can, if you want, you can answer in the comments what you think's gonna happen if you add H+ here. Okay, so something to think about. Cool. So this will work. again, we can be more selective and we can use something like LITBA to stop the reaction at the acyl. I was about to say acyl aldehyde. It's called the aldehyde. Aldehyde will be stopped with LITBA. And also when we think about Grignard or, organolithiums, it doesn't really make sense to do these reactions in 1EQ. You're really going to do them in excess. And if we do, what we make are symmetrical tertiary alcohols. Okay. Again, another thing we're going to see going on forward from this derivative is that from these derivatives that Grignards basically make tertiary alcohols. So is there a way to make a ketone, right? Is there a way for me to stop at the ketone? For the acyl halide and the anhydride, there is, right? That's going to be the Grignard, the Gilman reagent, R2CuLi, and these guys will stop at the ketone. This is really important, actually. So if we look back here, we didn't have any aldehyde synthesis, and we also didn't have any ketone synthesis, right? There was no ketone synthesis here either. So what that tells us then is that these reactions here are of utmost importance. If we ever see a ketone being formed, we really want to think that an acyl halide is being used, right? If we ever see an aldehyde being formed, although we'll see with all the derivatives, aldehyde's not very hard, but acyl halide is something I can consider to make the aldehyde. Okay. I guess the tertiary alcohol, again, also is kind of significant in that you can't get the tertiary alcohol from an acid. But once again, we'll see that these two reactions here, I'll give them a different color. These two reactions here are a little less important, just because, we can really make all of these. All the derivatives can really make these. So these are less important, but significant. This is more important and very significant. Okay, cool. So these are the reactions of the acyl halide and the anhydride. Just a bit of a reminder. If we go to the ester now, the ester being less reactive, now requires a little more catalysis in its reactions. But H plus H2O or OH minus H2O, which, pick your poison, it will give us the carboxylic acid or the carboxylate, right? So this is not something you have to worry about. So OH minus will give us the carboxylate. Acid will give us the OH. Okay. We can transform esters into other esters using, again, the H plus route or the OH minus route. Again, pick your poison on that. We'll call this OR prime. Okay. So it turns into OR prime there. Doesn't really matter whether you do this in base or acid, you will get the same answer. There's no anything like this to worry about. If we wanted to turn the ester into an amide, we could also do that too. This one's also a bit equilibrating, typically done in acid though. Don't really see a base condition for this. Okay, so we can get that there. Once again, if I use ammonia, if I use a primary amine, or a secondary amine, I can completely control for what kind of amide that I get. Okay, whether it's a primary, secondary, tertiary amide. Oh, I said earlier we can't make tertiary amides. I meant to say quaternary amides. That's what I meant to say. My bad. I will put a note that I misspoke there. Cool. So you might be thinking, okay, as we went from halide to ester, we kind of reduced the number of reactions, right? Like acyl halide, if you might remember, it can make every derivative. Anhydride can make every derivative but the acyl halide. Ester then it can only really make the amide. And so you might be thinking, oh, okay, so there's not very much transformation on that end. But keep in mind that we still have the ester enolate reactions as well, which I'll put on the side here because they really do deserve their own section. So if the transesterification reaction, which is this one, requires that we use R prime, right? I should have wrote that. This requires R prime. If instead I use RO minus, which is the same, right? So these are the same, right? These are different. Okay. Using the same gives us the ester enolate. And the ester enolate is a pretty good nucleophile. Couple things that we can do with that. We can react with Rx to give us an alpha transformation on the alpha on that alpha carbon. Okay, so alpha carbon here, alpha carbon there. You can add Rx and we can get that. We could add, let's add formaldehyde, right? We're adding formaldehyde. Oh no, let's do this. Let's put R here. Okay, actually, let me just make it ambiguous for now. Okay, adding this gives us a carbon and an oxygen. Okay, so we add a carbon-oxygen bond there on that alpha carbon. Now, depending on the identity of this, we get different levels of alcohol. If I use formaldehyde, I get exactly this answer here. Okay, if I use some kind of acetaldehyde derivative, I will get this answer here, right? And you can imagine if this also becomes R, then I'll get an answer here like this. Okay, so imagine you see, your end product is an ester, where on its alpha carbon, we add a CO bond. And I will, again, make it very obvious what I'm talking about. I'm going to color it. So imagine a CO bond being added, right? A CO bond being added. You know for a fact that this is a ester enolate adding on some kind of carbonyl. If we can add carbonyls, then we might as well add epoxides, right? Because epoxides are the same kind of electrophile. And once again, instead of adding one carbon, we're going to add 2 carbons and then an alcohol. Okay, so 2 carbons and alcohol now in this transformation. So 2 carbons, oxygen, 2 carbons, and an oxygen. Once again, if we had an asymmetric, right, that just means that we're going to attack on the less subside. So the R group would go here. So imagine you have substitution here, right? And we have this R group, flying out. Don't think this is a ketone or an aldehyde. Don't think it's like a ketone or something, right? This is 2 carbons and oxygen. That's clearly an epoxide form. Okay, this is an epoxide here, where one of the carbons on the epoxide has this methyl group here. Okay, this is more of a 1/8, final version. Like in the final, we would want to know this, but I'm still going to include it. But we can also add enones. And so you have to bear with me a little bit while I draw out how this would look. But we're going to add 2 carbons and then a carbonyl. Sorry, 2 carbons and then a carbonyl. Okay, and this is what it would look like if we added an enone. Enones, it's more, it's better to just look at the relationship that it forms. We're going to form a 1,4 relationship, right? Or you can think of it as a alpha, beta, delta, gamma relationship, right? So alpha, beta, delta, gamma relationship. That's what we're going to get on that one. This is not very likely for you guys to see this one. This one's more for the final, I would say. The very last thing that we can add that would be of significance is an acyl halide, which is a little bit interesting. But basically, this is an acylating agent. This acylates on the alpha carbon. Okay, so if you see that CO fragment, but we have a retention of the carbonyl, so this CO fragment gets rid of the carbonyl. If we have a retention of the carbonyl in the CO, then it's an acyl halide. Okay, this is sort of makes this reaction here, like you could have thought that, hey, if this is like let's say this was like an aldehyde that we added, right? Let's say we added an aldehyde, so that's only a primary alcohol here. Sorry, a secondary alcohol. You could oxidize this into a ketone, right, with PCC. But we could also just add an acyl halide and accomplish the same thing. Okay. So a little bit of some interesting stuff there. So those are just reactions, right, that we want to know. We can also do reductions on the ester. Again, lithium aluminum hydride is going to destroy everything. So this will turn this into a primary alcohol. But just keep in mind, right, that NaBH4 will not work here. NaBH4 will be NR. Only lithium aluminum hydride will work. Since dibble is a derivative of lithium aluminum hydride, but it only has one H, we can stop at the aldehyde. And so once again, what I mentioned before, right, like we have this guy here, not as significant as a reaction because we can also do it from the acyl halide. So that's kind of like, okay, that's cool, I guess. We can also react with Grignard, or we can react with RLI. Again, doesn't really make sense to do these in 1EQ, but we're really going to do these in excess. These are going to give us the tertiary symmetrical alcohol. So once again, not a very significant reaction, right? These are less important, right? Again, we can make this very easily, right? These two from the acyl halide as well. Ketone is really the one that we're like, how do we make ketones? Can't do it from an ester, unfortunately. So esters cannot make ketones. Okay, so this is sort of like all the reactions you want to be aware of for the ester derivative. Okay, and it's really, these guys here are really iconic. You can really tell, if you see like any alpha transformation or change on the alpha carbon is really telling that it's like an ester enolate. Oh, that actually reminds me, I did forget one reaction for the carboxylic acid. Probably one of the more important ones, the HVZ reaction. So we can have HVZ here. And HVZ, right, adds the bromine alpha. So what is it, PBr3, Br2, something like that. It adds the bromine alpha to the carboxylic acid. Now we can do a couple things here, right? We can add an amine here, and we can make an amino acid, right? This is here. Does anyone know what this is? Does anyone know what this amino acid is? If you get this right, you can write in the comments. You can write your guess. If you get it right, I'll give you 20 pre-med points. How about that? 20 pre-med points if you know which one this one is. Okay, you can cash them in for absolutely nothing, but there you go. Maybe the first person to get to it to 100 pre-med points, I will give you 1 hour free of tutoring. Anyways, this was glycine. That was pretty easy, I think. Glycine there. Oh, sorry, I didn't mean to erase that. But yeah, we can make amino acids with HVZ, although no one really does HVZ anymore because it kind of sucks because this actually takes 3 days at room temp. But it's really one of the only ways you know how to transform on the alpha carbon or make an alpha carbon electrophile. That's really the important here. This is an alpha carbon electrophile. So we can react nucleophiles with this guy here. So if you see a potential nucleophile on that alpha carbon, you know that this probably was the result of an HVZ. Some other things that we can do is we can add, like, for example, I think bicarbonate and water will do this. You can make alpha hydroxy acids. And these guys here, alpha hydroxy acids, are a little bit, you can do quite a bit with these guys if you really think about it. I think you need to have the H version of this actually. So yeah, I think it has to be this. Okay. But you can do quite a bit with these guys if you think about it. Like, I'll give you a couple ideas, but imagine if you did Jones or PCC on this, right? What do you think Jones or PCC would do in these situations? That's something cool to think about. You can also, this one's a pretty interesting one, NaCN DMSO will substitute this into a nitrile. And nitriles, we can do a lot with nitriles. We're going to see all the reactions we can do with the nitrile. We can do quite a bit. So the nitrile is going to be an interesting thing there. Okay, but HVZ, if we see a nucleophile on the alpha carbon, right, or something that could have been born from a nucleophile on the alpha carbon, we want to think HVZ. Ester enolate is really if we see electrophiles, right? So, or things born from electrophiles, like alkyl groups are born from alkyl halides. That's an electrophile. So ester enolate. Alcohols that come from carbonyls, epoxides, enones or acyl halides, right? Like those are electrophiles, right? Alpha carbon transformations that add electrophiles is a really ester enolate idea. Okay, so a way to kind of separate, how do I know if my transformation, let's say I have derivative X here and I have transformation Y, right? How do I know if it came from the ester enolate, so the EE, or the HVZ? If Y came from a nucleophile, right, then it's HVZ. If Y came from an electrophile, it's ester enolate. Okay, and we'll see. Don't worry, I'm not gonna just throw this on you and expect to understand your own. We'll do a couple examples where we can see this clear distinction. Okay, so all that leaves us with is now the ester and the amide, which I'll put on the same page. I think we either hit or we're at the 1 hour mark, so I think we've made pretty good pace, which I'm happy about. Cool. So what we'll do now is just talk about the ester and the amide. Sorry, the amide and the nitrile. But for the amide, we're gonna have to talk about 2 different versions of it. So I guess we kind of do have to fit like a couple different things here. Let's see how much space I can make with the primary amide, and we'll go on with that. So primary amide, really can only do one derivative transformation. If it's a primary amide, we can do SOCl2, and that gives us the nitrile. That's it. That's the only real derivative thing we can do here. We can always hydrolyze this, whether it's an acid or base, doesn't matter, right? Again, really what's only thing that's going to matter is if if you use acid, you get the carboxylic acid. If you use base, you get the carboxylate. That's it. That's the only thing that's going to matter, right? So I'll even highlight it there, right? This is what we're going to get. But that's just about it in terms of doing derivatives. All we can really do with primary amides is, reductions and one really special reaction. Okay, so if I do again, lithium aluminum hydride, surprise, surprise. Oh, wait a minute, this doesn't make an alcohol. This makes an amine. So the lithium aluminum hydride reaction is cool in that it kind of just shaves off the carbonyl because the O group is a better leaving group than nitrogen. In all the other derivatives, the Y group tends to be the better leaving group. So Cl, carboxylate. In this case, it's O and O, so it doesn't matter. But O versus N, O is always the better leaving group, or it always derives the better leaving groups. So in this case, lithium aluminum hydride will actually destroy the carbonyl and actually keep the amine. Pretty interesting result there, in my opinion. Pretty surprising result. If we used Dibble, 1 EQ of Dibble on a primary amine is actually not going to give us the aldehyde. It's actually going to give us the amidate. Okay, we're going to get the amidate. So that's a little bit interesting. You might be thinking, oh, what's going on? Same thing with the carboxylic acid, in that an acid base takes place before we do the reduction. At 1 EQ, where Dibble only has one hydrogen, tough luck. You're only getting that one deprotonation. Again, with 4 equivalents, we can just use lithium hydride and allow that to destroy the molecule, but not going to be the case with Dibble. Okay. You can imagine LIPA does the same thing, but did I write LIPA here? No, I did not. Good. LIPA isn't really used for amides and esters. Dibble is what's really used. Okay. We could do the Grignard reaction. Again, RLI or RMGBR in excess, as always, is the better thing here. Well, actually, at 1 EQ, let's do the 1 EQ one first. 1 EQ, this is really only going to do, again, another acid base. So this here is also, you can realize this is going to mimic a lot of the carboxylic acid here. It's really going to give us this. Okay. So primary and secondary amides that have that NH bond, they really only do acid-base reactions, which kind of makes them a little bit annoying with any sort of basic entity in their presence. If we were to use, I didn't talk about this for amides, sorry, for esters, but I'll talk about it now. Gilman, right? Remember the ketone reagent for acyl halide and anhydride? Gilman's not going to work for amide or esters. That's why I didn't even mention it for the esters. So you really can't do anything there. But there is one reaction that's of really important significance, and it might not seem like, as much at first, but Br2 NaOH H2O, or like halo form sort of reagents, what they do is they completely decarbonylate an amide. And so this reaction is super important. It's so important. I really want to emphasize this. Remember that primary amides can be made from any derivative, right? Any derivative can make the primary amide, and the primary amide can be turned into a primary amine. So what I want you guys to realize is what this tells you then is that given any derivative functional group, you can completely swap that out. You can swap out COX for N completely. So this is your first exposure to making an amine. And it's how you can think about for midterm 2, how Nassiri might tie together a chapter 1920 synth with a chapter 2021 synth. She might make you make a primary amine and then do primary amine chemistry on midterm 2. So yes, this is very relevant to midterm 2, but this is also very relevant to midterm 1. Because hey, we can completely transform a whole carbonyl or whole derivative into an amine. So we will see this happen. So that's why I really want to highlight this now. This is a very important reaction. Okay, but that's what primary amines can do. Again, this is only a primary amine can do this reaction. Okay, for a tertiary amide, sorry, I think I said amine here. I meant to say primary amide. Only primary amides can do this reaction. For a tertiary amide, we can do pretty much all the same stuff, but now our Dibble reaction makes more sense, right? Because now we can do aldehyde here. Our Grignard reaction makes more sense. Right now we're doing it in excess, no proton to worry about. Now we're going to get the tertiary symmetrical alcohol. Okay, lithium aluminum hydride going to work exactly the same. Yeah, pretty much everything the same, but tertiary amides just have the ability of not having to worry about acid base, and therefore Dibble and Grignard works well. There was that one little, again, I don't really think any of you should be doing this unless you really don't like, you can really, if you feel like your grade is in a good spot, you can use Wainwright amides to make ketones. So RMGBR here will give you a ketone of your choice if you use the Wainwright amide. What's the Wainwright amide itself just comes from the O-methyl hydroxyamine with acyl halide. So this here is, you know, for those of you that really want to impress your TA or Dr. Nassiri, you might want to use this if you can. It's sort of like the one exception to, oh, only 2 groups can really make ketones. Really, there's 3 groups that can make it. Okay, cool. All right. I think I left 2 blank there. 2 is just an acid workup. So that's just what the tertiary amide gives you access to there. All that leaves us now with is the nitrile, which again, only accessible from the primary amide. Acids cannot make directly nitriles, but we can make them from the primary amide. And with these guys, again, really the importance is the reduction reactions. You can basically think of nitriles as our access to functional groups that are kind of, you know, I don't want to say not allowed, but they're a little bit hard to make with the other derivatives. Dibble will give us the aldehyde as it did with everything else. Lithium aluminum hydride basically just turns this into a primary amine. If you're having a hard time seeing this, you can pretend this is H2PD. H2PD also works. Remember that H2PD is just really good at hydrogenating high bond orders, especially something like nitrile is going to be not particularly hard. Lithium hydride can reduce pretty much any heteroatom pi bond just because of how reactive it is. But this will just make a primary amine. It's like you're adding 2 H's here and 2 H's here, right? That's all you get there. Really, the coolest thing about nitriles is its reaction with Grignards, because in this case, we do actually have complete control to get to the ketone. So remember how I said back here that this was a really important reaction. You guys need to remember it. Only acyl halides and anhydrides and nitriles can make ketones. So if you ever see a ketone being formed in the reaction, like you want to think this, right? Like you want to at least give a thought to the nitrile. And we'll see acceptable places where it's acceptable to think that. Okay, nitrile is going to be really important in that. But again, you know, really, if you wanted to get the, you know, anything else like a derivative, it's either going to be, you know, it's really only going to be the carboxylic acid you can get to. I don't really see a point in doing this, honestly. Like, I don't see a point in doing this unless, you know, you need to turn the, like you started from a nitrile and you needed to turn it into another derivative, right? Like let's say that this was your synthesis. I mean, truly, the only thing you can do here is turn this into a carboxylic acid and then do a reaction here, because that's the only way to access the derivatives. But it's like, what's even the point? In my opinion, I don't really see the point here. Cool. All right. So now that we've done a very brief and quick overview of all the reactions that we would want, so you can think of this as like a mini reaction review of all the things that are allowed. Now we can start to get into the synthesis. And as I said, we're going to come back here, you know, to all these pages, these last 8 pages of work, and we're going to see what is allowed and what isn't allowed, okay, and what we should be thinking about. So we'll start off relatively easy in this synth practice now, okay. But we're gradually going to go higher and higher in difficulty to a point where, you know, you're probably going to end up not trying these and just listening to what I have to say. But hopefully you give every one of these problems a try. So what I would recommend, in my opinion, the best thing to do is try the problem on your own first, and then, you know, see what I've done. That's how I would do it. And I think that's going to provide you the most amount of effort, or most amount of like work, and most amount of like, you know, learning in this process. Okay, cool. So let's just go ahead. Let's just start. Just start with something. Okay. So again, try this on your own. Note what you need to note, and just give it your best, right? And once you're done, you can, I would recommend pausing and trying. Once you're done, unpause and let's see if we can come with the same answer. Okay. Cool. So hopefully you did pause and you try this, and if not, it's okay, because sometimes we need someone to help us build the base as to what to think about for synthesis before we can do it. So one thing I mentioned is that I have a very different approach to synthesis. I have what I call, or not what I call it, but what is known as the retrosynthetic approach. And so I will offer that approach first, because it's my way of doing it. I think it's the best way of doing it. And then I'll try to do it more of what maybe you guys do, which is more like a forward approach. But what retrosynthetic approach is we look for relationships in the final product that can help us explain where certain bonds came from. For example, one thing that we should know about derivatives is that any derivative we have, we can cut between the carbonyl and the derivative group. And we can basically have said this came from, let's say, like a carboxylic acid and the derivative, right? And the derivative group. Or essentially, we're saying that we can cut here and say that there's some Y group, and then there's some X group, right? That's a very good one. Typically, Y is equal to OH, right? Because carboxylic acids can technically make every single derivative. It can also sometimes, most of the times it will be Cl, right? Cl is like a very good option because, acyl halides are the most reactive derivative, so it can make practically anything. I like to start off with the OH to see where that gets me, and see if it works. So for example, the first thing I notice here is, hey, there's an ester here. Let me go ahead and cut here, right? Because I can cut between that derivative group. So I know that we maybe did like an esterification here. Okay, well, cutting that, again, will give me the carbonyl group, X, and then OH like that. So this is what I get out of the reaction. Okay, now again, X could be OH or it could be Cl. You could really choose either one, but notice something is that if this were Cl, right? If this were Cl, so like I said, this had to be acyl halide. What do acyl halides come from? Like, how do we make acyl halides? So when we cut here, what are we saying we're going to make? It's going to be some group in Cl, right? The only thing that can make acyl halides is carboxylic acids. So it's not that it's a waste in a step, and I don't think it's ever a waste to make an acyl halide, but notice how we could have just started from the carboxylic acid anyways, and we know that this reaction is acceptable, right? The reaction of an alcohol and a carboxylic acid. This is just a Fischer esterification. So when it comes to like esterifications, I would say carboxylic acid is fine. Really, the only reaction where Y has to be Cl is if we're making an amide, right? Because only amides struggle in their reaction with carboxylic acids, right? Amines and carboxylic acids don't really make amides very well. Okay, but here we can see clearly this came from a carboxylic acid and alcohol. Now the alcohol, we could figure out how to make that if we wanted to, so I'll keep that off on the side. But notice how we start off with the 4-carbon chain, and we end up, with this 3-carbon chain. So this retrosynthetic approach does use a little bit of forward, although the forward is just looking at the starting material. If I started with 4 carbons and I ended with 3 on the carboxylic acid, right? Which synthesis is this? Which reaction am I doing here? Okay, and so I will give you the powerful hint. I will go back to the slide. Hopefully you guys were taking notes too while you're doing this. But like if we look here, the first mention of a loss of 1 carbon was the haloform reaction, which just required a methyl ketone. So as long as there is a methyl ketone being made, we can do the haloform. So now I can say, hey, loss of a carbon, right? This is probably haloform. And so that just means that I replace the OH with a methyl ketone, right? And now to go from 4-carbon chain to 4-carbon ketone like this, again, think back to how do we make ketones in general? They typically are born from alcohols. Okay, right? This is just a PCC step. Well, how do I, add an alcohol to this secondary position here? I can't just straight up, add an alcohol, but maybe I remember that, hey, when I have an alkyl chain, only an alkyl chain, the only reaction I can do is Br2HV. So I get here. And then to go from here to here is not too difficult. Now, you could do two things here. You could do a water addition here to do like an SN1 type reaction. You could also do the acetate substitution, which is more 118C relevant, I suppose. So that's also available to you. Okay, you can do this as well. It doesn't really matter. You're going to get this answer anyways. Okay, so this is what I like to do for synthesis, working my way backwards, because maybe going forwards might stump me. Like maybe what I could have done was I could have noticed, oh, okay, it looks like there is a carboxylic acid coming off that one end of the alkyl chain. So maybe what I could have done was done this and then realized, okay, I need to on the end there. So I do that and I do this. You can think about how to do these transformations. It's not particularly difficult, I don't think. And then maybe you do whatever synthesis you need to do and you get the carboxylic acid there. And then now you're at this point where, oh, this is 3 carbons, but this is 4. I need to somehow get rid of this carbon. So I'm not saying that everyone will make this mistake or that it's a common mistake. I'm just saying that it's a mistake that could happen if you just move forward. I think going forwards affords too many mistakes when just going backwards can help you really identify what functional groups are going to for sure show up, right? Now, again, I did say I would offer a forward approach, and the forward approach is very simple that you could do here because you'll realize it also does use retrosynth, but you could initially just realize that we went from 4 carbons to 3 carbons. So that tells you it's halo form. So you could have worked your way up to get the methyl ketone and then done halo form and then just realized, okay, carboxylic acid to ester. Okay, that's just going to be Fischer esterification. Okay, so that's like a forward approach. But again, it does require a little bit of retro because you have to think, okay, 4 carbons to 3, that must mean that at some point that this was a thing, that this reaction happened in the past, right? So work your way up towards the methyl ketone and then do the halo form and do the Fischer esterification. Cool. Now I did say that we could try to make this guy here. It's actually not that hard. It requires a little bit of extra thought, but we have a 2 carbon chain and an alcohol. So from the starting material, we need to get rid of 2 carbons. Now, if you look at it, it's a 4 carbon chain. So cutting down the middle will give us 2 carbons. Another way of saying this is, hey, if I wanted to somehow turn this into a 2 carbon unit like this, I could just add a double bond, like I mentioned, and I'll cut right in between. The only thing is that this will give us aldehydes. Right. Well, that's pretty good because aldehydes can be reduced and ABH4 is pretty good here. And that would give us alcohols, right? Exactly the alcohol we need to do the reaction. How do I make the double bond? Double bonds typically come from halides, which again is the only reaction I can do here. Now, to get the internal double bond, we use a small base. So for example, we can use an RO minus here, or OH minus will work too. OH minus here would be probably pretty good. Okay, that will give us the internal double bond. If I wanted the external double bond for any reason, I'd have to use a bulky base. Terbutoxide is the good choice there. Okay, cool. So this one's a nice one. We can really make everything from this one material. Okay, and I always think those are the best syntheses where they force you to think about how we can make everything. Okay, cool. So first synthesis down, and hopefully the thinking is also getting it's starting to become a little more helpful to you guys. Let's go ahead and try this synthesis. And we're going to try actually 2 versions of this synthesis. I want you guys to try this version. And if you have the time, or if you want to first see you can first look at the answer for this one, but I would like you guys to try this version of the synthesis as well. Okay. So try both of these and see what you can do. Cool. So hopefully you guys paused and tried at least one of them, but let's do the first one. So again, retrosynthetically, I like to look at the starting material and think what bonds do I know for sure could have formed, right? And the bond that I know for sure could have formed is the amide bond. So that's like the easiest bond for me to cut first, noticing that, hey, this is an amide, so I know I can cut here. So once again, what did we say about, derivatives? They typically come from another derivative, like an alcohol, like an acid, and they come from the group that we have. Now, keep in mind, right, if this is an OH here, right, remember, amides aren't really well formed from carboxylic acids. They're the one derivative where forming it from an acid is not very good. we typically want to do it from the acyl halide. So this is the one time where, or one of the times where doing, or using an acyl halide is probably going to be our better bet here. Don't really want to use the carboxylic acid. So that means that we just have to do 2 of these cuts here, because again, the only way to make an acyl halide is from the carboxylic acid. But we have to go through this, right? Because carboxylic acids are just really terrible at making amides. Okay. Once we're here, right, we can start to employ a little more of the forward synth, where we notice, okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. So we added a carbon. So if we added a carbon, let's go back and see when was the first time we saw add 1 carbon. We saw it here. Remember, this reaction is obsolete. 118C has a better way. So let's go to our 118C slide. And now we have 2 ways to make 1 carbon or add 1 carbon. We can do the Grignard or the nitrile. So Grignard or nitrile. Now keep in mind, really the biggest issue with the nitrile is that it's sp2 bound, right? So tertiary substrates are pretty much a no-go. sp2 sp substrates are a no-go, but basic substrates are okay. Grignard kind of does well in everything, just basic substrates are bad. So based on our molecule, which looked like basically a long chain, it looked like a fatty acid. It shouldn't really matter which one we do, right? Because there is no, they're both primary carbons upon which we add the acid. They're both sp3 hybridized, and there's no basicity component at all. So we can really do any one we want to. Okay, so it doesn't really matter which one we use here. You can use whichever one you want, but we're essentially saying that this must have come from something. I'm just going to go with the Grignard synth. Okay, and if we did the Grignard synth, how do we make Grignards? That's just Mg ether from the bromide, right? And if we're forming the primary bromide from an alkene, how do we do that? That is HBr-ROOR. Okay, so this is a very acceptable synthesis that we can do. Now imagine if I change this slightly. Let's say that I turned this into an alcohol here. So we have an alcohol here. How do you guys feel about this synthesis now? Does this synthesis still feel very viable to you guys? Hopefully you're thinking, no, the synthesis does not feel very viable anymore, because Grignard is going to destroy that proton all the way on this side. So we can't use Grignard for this reaction here. We're gonna have to use the nitrile. Okay, but we can do a hydrolysis here and then continue on with the reaction. Now, another thing to consider is that SOCl2, if we have a carboxylic acid and we have an OH, both of these alcohols could react with SOCl2. So really, if we did this reaction, we're probably going to end up with this here, because SOCl2 would react with both of them. Now, this is just something more to think about, right? Rather than a synthesis question. I don't think you'd ever be asked this, but a good thing to think about is, who do you think is going to react first? Who is the better nucleophile, OH or carboxylic acid? The answer is it's going to be the OH that reacts first. Okay, so in reality, the very first intermediate we're going to have is this guy here, right? Because OH is more nucleophilic. This lone pair is more basic, right? It's more available, more localized on this oxygen surface, as opposed to this OH. It's not as localized. It is delocalized, right? So OH is always a better nucleophile than COOH, and therefore this OH is probably going to react first. This could be a very good predict the products question. Very good predict the products question. So keep that in mind for PTP. But in general, right, they're probably not going to force you to do that. Maybe instead what will happen is you'll be asked maybe to do this, to make this ester here. So that now when we do the cut, we can go to OH instead and say, okay, OH, and then HOR, right? Again, this could have still have been an SOCl2 step, not to say that it can't, right? But we're probably not going to do SOCl2 until the very end, right? Because if we do SOCl2 here, right? Well, actually, no, we could. Never mind, we could. We just have to be careful and say 1EQ SOCl2. We could do 1EQ SOCl2 here. And so that will turn this into Cl. But in my opinion, the better thing to probably do here would be to do the esterification first and then SOCl2, just to make sure. So in my opinion, the better process would be to first do Fischer esterification and then do SOCl2. right? Because Fisher esterification is very specific to this guy here. Acid and alcohol is not really going to mess with this guy. You might think that you could do a ether formation. So a couple of you might think, oh, could an acid protonate on this alcohol here and then the other alcohol attack? And so this is a really good point. This is something to take into consideration. But if either one of these is protonated, although this one might be easier, alcohols are known as hard nucleophiles. Don't worry about this point here too much. Just want to tell you. And typically hard nucleophiles is given the choice, would rather react with a hard electrophile. The harder electrophile is the carboxylic acid. So really my only point there is just to mention that, in general, it is just going to be better for the alcohol to react with the carbonyl. But if you're worried, you can, or sorry, not that if you're worried, if you were worried that the Fisher esterification would compete, it's really not. I just want to really prove the point that, yeah, this alcohol is probably going to be okay in the presence of the Fisher esterification condition. This one here that I've drawn here is a lot harder than the first one, so don't worry too much. That's why I'm walking through it. Really what I wanted to get the point here was that there is an alcohol here, so it completely changes nitrile to, completely changes Grignard synth to nitrile synth, right? Before, like the one we did way in before it made this complicated, right? But this one here, you could have done Grignard on, right? Grignard worked really, really well. Nitrile worked well too. It didn't really matter. Okay, cool. So that's this one. Now I mentioned that you should try this one too. And again, if you're just if you like, please try it. I think it's a good problem to think about. Most of these intermediates here, you'll notice, are going to stay pretty much the same. So maybe actually we won't erase everything. But yeah, try this on your own. Try to figure out what this one is doing different from everything else. Okay. Maybe doing this is going to help you guys see what to do. So maybe pause and try this. So the hard thing about this one is when we get to this point here, and note, like thinking about which synthesis is better, like more viable, whether it's nitrile or Grignard. The best way to understand it is maybe skip this intermediate and think about the one that's always going to be before it. So whether you do nitrile or you do Grignard, you're always going to have this point here. And then it's a question of whether I make the MGBR reagent, so whether I make this, or whether I make the nitrile reagent. So ask yourself the question, right? Maybe go back to that criteria. Which one of these two makes more sense, right? So this is the criteria back here, right? Which one of the two makes sense? And I'll even draw it here, actually. So this is either going to be nitrile or it's going to be Grignard. Who makes sense in this case? So hopefully you remember that, okay, in terms of substitution, they're both primary on the carbon that holds the nitrile group, but hybridization is sp2. And who doesn't work for sp2? The nitrile, right? Nitrile doesn't work. So we have to do the Grignard synth here, okay? So it has to be Grignard that we employ. We cannot use the nitrile. And so what we get then is the vinyl halide. And again, how do we make vinyl halides? You really have to go back and look at the notes here. Where did we make a vinyl halide? We made it from the alkyne. So this one is a tricky one because you have to go through an alkyne to make the vinyl halide here. So it's going to be HBr, ROR. This gives us the alkyne. How do we go from alkene to alkyne? This is classic 118b, right? How to do this transformation here. To just remind you of how to do it, we would typically do a dihalogenation, and then we do a double elimination. So NaNH2 minus typically is the one that did it, right? We typically did it in a high excess, followed up by an acid wash. And what we would get is our answer, okay? So this one was a little more difficult in that we had to go through the alkyne. But again, the alkyne, what I want you to notice, the alkyne gives us the vinyl halide, which gives us access to the conjugated acids or the conjugated derivatives, right? The fact that the double bond is conjugated to the pi bond of the carbonyl is what's the important part here. So conjugated systems, you want to think this kind of stuff here, okay? Specifically this guy. Cool. maybe on an actual exam, you might start from here. You might not start all the way back here because this is like very difficult, right? But you never know what's game and what's not. Cool. So hopefully that makes a little more sense. Let's do another one. Okay, let's do this one here. And if I did not mess anything up, which I hope I didn't, go ahead and try that. If there's something not adding up, I probably added or subtracted a carbon. So I'll give you that hint there. If I messed anything up, I probably added or subtracted a carbon. So maybe if something's not working out, try to add or subtract a carbon and it'll work out. So go ahead and pause and try this on your own. So I just realized I did forget a carbon. I knew it. I forgot that one there. So I apologize. Anyways, let's go ahead and let's try to solve this problem. So once again, I know the cyclic ones make you guys really scared. Like it's a really scary problem to ask. But hey, we know how to make derivative bonds. We know that a derivative bond can be cut here. And that we can say easily that, hey, this came from, right, some Y group and something like this, right? Just remember that for the cyclics, everything's on the same molecule. Everything's on the same molecule. So you just got to draw everything together. Okay, we can sort of say that this equals what, 1, 2, 3, 4, 5, 6, 7. So 2, 4, 6, 7. Right, and we get here, and you can kind of see where this and this kind of come together, right? Make each other. Let me actually switch this so it looks more like the starting material, right? So hopefully now looking at this, it makes a little more sense where I'm getting my material from. Now again, Y could be Cl or O. When it's an ester, O works very fine. It works well here. Acid is okay, because this is just a Fischer esterification essentially. Okay, but this is an intramolecular Fischer esterification. All we did was we cyclized this intramolecular molecule. Okay, to continue the rest of this, right, it just becomes a question of, you know, how do I make this acid here from this bromide? And again, we could do the counting of a carbon. Probably most of you probably did that first. 1, 2, 3, 4, 5, 6. So 2, 4, 6, 2, yeah, and then 2, 4, 5. I added a carbon, right? I added one carbon. This is clearly nitrile or Grignard synth. But again, ask yourself, right, which one would fail? So if you haven't already written this down, please write this down, right? Pause and write this down. But which one would fail on that one? The answer is, because there is a basic group, Grignard fails. And so we have to do a nitrile synth here. This question was actually asked 2 summers ago, I want to say, 2 summers ago. And the unfortunate thing here was that when it was asked, people wrote the Grignard synthesis and they got full points for it. Like the TA messed up, they got full points for it. And then like a week later, once it was made known that people were getting points for syntheses that were not viable, a bunch of people lost points, and it was a very unfortunate situation. So always make sure, one, that you're doing your best that you can, right? And all, two, when you look at the key, make sure that your points match up with the key, because if they don't, and you see that you got points for something you shouldn't have, don't expect those points to stick around very long, because someone will find out that people are getting points that don't want, and they will tell the TA, and then the TA will have to go through everyone's exam very grumpily and regrade. Okay, cool. But don't worry, we won't have to do that because we're watching the synth guide, so we're going to get full points on the synthesis. Right? Anyways, so there's actually another way to do the synthesis as well, but not from this starting material. And I really want to show it to you guys. I think it's a really, really good problem. And it was actually, I was going to save it for the end, but I think that now that this is in our head primed, let's just talk about it now. So if you have to pause, take the screen or whatever, I'm just going to quickly erase this. But I want to show you guys that there's other things that we can do here too, that make this problem a little more interesting. Actually, you know what? Let me do this. You can actually start from here and make this whole molecule. So try that. This is significantly harder, by the way, just because there's a lot more steps and there's a lot more to think about. Okay, but go ahead and try that. And again, I will give you this first retrosynthetic piece here, just because we all worked on it together. So you guys deserve this piece. Okay. Actually, I will give you one more piece to this because it'll probably make it. It shouldn't be. It's going to be a lot harder. You're not going to know what to think about from here. But I will give you guys this piece as well. Okay, there you go. Now go ahead and try this on your own. So if you tried this, kudos to you. This one, again, is a really hard problem because it may not seem very obvious as to what you need to do. But this is a great example of where retrosynth and forward synth can kind of merge together and help you understand what you need to do. Because first off, right, when we look at this molecule here, and I think once you get this piece here, really what I wanted you guys to notice was that there is a relationship in here that I talked about before. So maybe if you couldn't try this now. There is a relationship in this molecule that you need to remember that we talked about that can really help you break apart how to do this. If you need even more help, I will give you this here, right? We have this relationship here, or we can do this one here. We can say this relationship here. Oh, wait a minute. Oh, I feel really bad. Okay, sorry, I messed up. I feel really bad if anyone tried this problem because I messed up actually. Oops, I will also write a note to not try this because I need to change this too. My bad. This is the one that I was talking about. This is the one that you can do. Okay, I will specifically write a note in the description that says, do not try this because 1, 2, 3, 4, 5, I can't count. Okay. So you can get from here to here, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, this needs to be over here. Okay. So we can get to here, and then again, I gave you guys this step here. So actually now you should try it. I think it'll make more sense. There's a relationship in here that you can take advantage of. And that relationship, right, was that alpha, beta, gamma relationship that I was talking about. Because remember, a gamma acid or a gamma ketone basically means that we can cut this beta gamma bond here and have said that this came from an enone. Again, how do we make carboxylic acids? Right, from this method, it's from the nitrile, right? This itself coming from the acid. Oh, sorry, from the enone is what I meant to say. This itself coming from the enone. And so the enone from here, right, we talked about how to do this. We can just brominate, right, do a substitution here. Again, remember, for a secondary alcohol, you need to do either H2O or do the acetate substitution. But we can oxidize this. You can do the acid halo form, and then a weak base E2. Okay, so my apologies. This one is really long. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it take me like a month probably to do this. 9 steps, but it's a nice problem. Again, paper chemistry, we can do as many steps as we want because we're just writing on paper. But this is a way that they can literally start you from nothing. And you can go all the way to something. Okay. So again, I apologize. I will make a note. I'm really, really sorry. I didn't mean to make it impossible. Okay. Hopefully none of you cried trying to do that, thinking that it was too hard. I mean, it really was too hard. It was impossible. So my bad. On that same note, I do want to try another ester problem that approaches the ester in a different way. Okay, and maybe once I've said that, that'll make this kind of obvious what I'm trying to do here. But imagine we went from this 5-membered to this 6-membered ring. Okay, so this is an interesting one, right? And I will say this: if you try to do this, in the way that I think you will, maybe you can come up with an answer, actually. Maybe you can. So pause and try this. And what I really will say is really go back to the ester tree, right? Really go back to the ester tree. Sorry, not the ester tree. Go back to these reactions here. Maybe I'll even tell you, maybe look at this page here. This page has a reaction that will make it really easy to do this one. Okay, so go ahead and try that. So if you took my advice and you went back to the tree, what I want you to realize was that esters have one interesting way of making them, it's from ketone to ester with MCPBA. That's how we get the ring expansion here. Because if you think about it that way, that it's MCPBA, then you go back to the 5-membered ring, because what you're doing is you're inserting that oxygen in to make it a larger size. You go to the ketone. How do we make ketones? That's just oxidation of alcohols. How do we make alcohols? That's just water. So we can do this synthesis very easily. If you try, I think a couple of you might have tried it the way where I've shown where you can cut the derivative, right? And I don't think that this would be wrong. Let's see if it will work. 1, 2, 3, 4, 5. So 2, 4, 5. Right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. So we would get here. 1, 2, 3, 4, 5. This would just be really hard to do from here because again, the only way to break a ring, right? How do we break rings? We would have to turn this into an alkene and then do an ozonolysis. But ozonolysis, while it may seem helpful, it's going to do something that's very unhelpful. 1, 2, 3, 4, 5. 2, 4, 5. It's going to give us a diketone. To get to the diketone, the dialdehyde, actually, to get the dialdehyde to the monoaldehyde is really, really difficult. There's no real selective reaction. And recall that Dibble, like the 1H derivative of lithium hydride or sodium borohydride, it doesn't really work on aldehydes and ketones. Really, Dibble only works on ketones, on esters and amides. LIPA could work. So maybe you might think LIPA, but remember that LIPA, really when we use LIPA, it's to make sure that a acyl halide or an anhydride reacts versus an ester or an amide. The point they're trying to make here, if I'm being a little bit confusing, the point they're trying to make is this is impossible. Like you can't really get a selective reduction there. And even if you could, you're probably going to run the risk of also just getting this, because if you could reduce once, how do you know it's only reducing once on every chain? Maybe it's going to reduce twice on a chain. You don't know. So it's just really hard to do this reaction. So hopefully if you tried it this way, you would get to this point and get a little stumped and realize it's not the right way. Ring expansions are very, very clearly going to be oh, wait a minute. I think I messed up actually. Oh, I did. Okay. Damn, 2 mess ups in one video. That's crazy. So actually, this might be possible. Oh, actually, no, it's okay. This is actually okay. This is actually funny because this is even worse. So even though I made the aldehyde on accident, this is even worse because what you're basically saying is you're reducing one guy and you're oxidizing the other, and that's actually impossible. So even though you could have maybe made the argument of Dibble or LIPA to reduce one of these guys versus both of them, this is actually just impossible. To do one oxidation and to do one reduction and one oxidation, that's impossible. So this problem is made even worse, even if I fix my mistake that I said earlier. So unfortunately, no, it's not going to work out as well as you'd like. But hey, it's okay because I'm now showing you that if we see a ring expansion, just think of MCPBA, especially if it's an ester. Okay. Now, the only way this problem gets harder, right? The only way this problem gets harder is if they decided to open up the ring afterwards. So let's say that they just decided to open it up. So 1, 2, 3, 4, 5, 6, right? So 2, 4, 6. And this is what they presented to you as the final answer. So imagine that this was not the final answer. That they said was go from this bromide to this alcohol here. Hello. Okay, my bad. Again, to do a ring opening, especially, from that, it always doesn't, I guess it doesn't really increase in size, but to do a ring opening, really there was only 2 ways, right? One way is doing the ozonolysis reaction, which again would give us, I guess you could get a diacid if you wanted to, but we could do the dialdehyde or the diacid depending on how we open that up. And then again, getting from here to here, very, very difficult, right? Because again, we can't just oxidize and reduce one carbonyl, right? It's going to either oxidize both or reduce both. There's really no way to control that. So ozonolysis is not going to be the best way to do it. Really, you have to be clever here and think about how, hey, if I have an alcohol and an acid on the same, molecule, that means that I could have come from a cycle, right? And so again, if that is difficult for you to think about, don't worry, because I am telling you now you know to think about it, right? Now you know to think about, hey, if I ever have an alcohol and acid on the same carbon, I can think to myself, okay, there is a possibility, that it could have come from the NCPBA reaction, the ring expansion. Okay, so again, a lot of synthesis is for you to get practice, but some of it's also just to get exposure to things that can work, right? This is one of those things that can work. All right, cool. Hopefully this segment wasn't too confusing. I apologize. I made mistakes about making mistakes. So I would believe you if you told me that, oh man, some of the things you said weren't the easiest to understand. Cool. And as always, always just type in the chat. Let me know how things are going. What needs more clarification? Cool. So I would say the synths that we've done currently have been about easy to medium-ish. We really haven't done a synth, in my opinion, yet that has been very brutal or really, really, really forces you to think. So with that being said, we are now going to do one that's a little more brutal. Okay, this is one of my favorite synths that's popped up in the past years. And it's going to go completely to the left field on reactions to think about. Okay. So the main reasons why I like this synthesis is because it actually uses real life things. This is known as naphthalene, this dibenzene, and this amine acid, or this amino acid here, is known as anthranilic acid. It's not an alpha amino acid, right? It's a beta amino acid, so it's not one that, it's not something you would learn in biochem, but it's a natural product that does exist in the real world. Okay, so go ahead and try this. And again, what I would recommend for this one is you can do a retrosynthetic approach here, but I would recommend a little bit of forward and backwards. And I really want you to think about, again, how do I make the acid? Okay, so go ahead and try this. So hopefully you pause and you try this. Again, main thing to point out here is how do we make the acid? Remember, I want to make the argument that making the carboxylic acid is really the hardest thing. And you can really see that, right? It was making the acid that really defined the last few problems that we've done, right? How do we make the carboxylic acid? And so again, I'm going to ask you, how do we make this carboxylic acid, especially from this molecule over here? Maybe it'll make it easier if I told you that this is a benzoic acid. Okay, what if this is a benzoic acid? So if we go back, how did I make benzoic acids, right? Looks like I made benzoic acids. My bad, my phone is going off. Let me just mute that real quick. I make benzoic acids from KMNO4. And remember, as long as there is a benzylic proton, we can have a benzoic acid formation. So this one is a little bit interesting because you have to do a little bit of forward and backwards. The fact that we have a benzoic acid means that we look for the hydrogens that would oxidize. There's two of them, right? Don't forget there's two of them. And so if I do KMNO4, H2O, OH minus, and heat, right? Followed up by an acid workup, I'm just too lazy to write it. What we're going to get is the dicarboxylic acid, or the dibenzoic acid. Okay, and so this is the important part, is that there's two of them, right? Because one of them, it sets up the answer for this guy. So our answer is set up for that guy. But this guy here, right, needs to turn into an amine. So again, I encourage you, go back in your notes and look, what reaction replaced an acyl derivative into an amine? What series of reactions or single reaction replace an acyl derivative for an amine? You might remember I made a big deal out of this one, right? So I will go ahead and go to the page that's relevant. Or did I miss it? Yeah, I did. So which one was it? The halo form for primary amides. Primary amides can be completely transformed into primary amines. And again, since everything can make a primary amide, then any derivative can really make a primary amine. And so now we can do a little bit of retrosynth because we can say, hey, if this guy got turned into this guy, then that must mean that before there was a primary amide here. Okay. And so the question just becomes, how do we make a primary amide, right? How do we make a primary amide? Again, amides can really only be made from acyl halides, right? That's the most efficient way. We can't do it from a carboxylic acid. So when we do this cut here, right, and I have this Y group here, right, really what that's going to be, that Y is going to be probably a Cl, right? A Cl will work here too. So I can use SOCl2 and say, hey, I will form the acyl halide from this. Now, here is the bit of the interesting thing here, right? And I think you guys won't see it until I draw it. But although this is the intended intermediate here, right? The intended intermediate to do this reaction. So I'll erase this part here. But this is the intended intermediate so that we can get the amine form, the amine to attack it. Notice how the carboxylic acid is right next to this acyl halide. So this one's a little bit of an obscure reaction, but it turns out actually, instead of forming the acyl halide here, or not that it doesn't form it, but instead of isolating it, what we isolate is the anhydride, because this intermolecular reaction here is a lot faster than the intermolecular reaction between, or the reaction of making the acyl halide and then introducing amine. The carboxylic acid's already there, so it will turn this into an anhydride. Now, don't worry, this is not a big deal. We could have also gone, here with heat. That would have worked too, because dioic acids are very good substrates to make anhydrides. Remember, anhydrides also react with amines, right? They also do that reaction with amines. And so nothing really matters here. It doesn't matter whether you thought about it through the SOCl2 pathway or the anhydride pathway. We always get what we want. So the reason why I love this problem is because, well, one, again, it's real life products, but two, you are directly rewarded for knowing, everything about, just knowing the most significant reactions, knowing that, benzoic acids are born from KMNO4 and some benzylic hydrogen, knowing that an acyl group completely swapped over to an amine is Hoffman, and then just figuring out how do we make primary amides in the first place, SOCl2. Now, I'm not sure how the point distribution would have went if you drew this out and then drew this. I know, though, that if you drew the anhydride, I mean, that was part of the intention was to draw the anhydride there. That would have gotten you full points. But yeah, I think that as long as you showed your reasoning, I mean, it's a really good problem. So one of my favorite problems from the recent years, that one. Cool. So again, that was a little bit more of a difficult one. And so let's keep that rule of difficult problems. Okay, let's keep that rule of difficult problems. Let's do this. Okay, so this one's a bit of a difficult one, but again, think about what's going on, right? Maybe there's already a couple of reactions you already kind of see that you want to do, and you try it out. Okay, try it out. So go ahead, try that out. So once again, you could work with what you already know how to make, right? Like the fact that you see an ester here. But one thing that we should also assess is relationship, right? And what I mean is we should assess the fact that there's two carbonyls here, right? There's two carbonyls here. Whenever you have an ester, remember, esters can do the traditional reactions of reduction, the traditional reactions to the amide, right, to other acyl derivatives. But esters also had, remember, they also had that whole field of reactions right over here that concerned the analyte. And the analyte, remember, the analyte was interesting in that it could add electrophiles to the alpha carbon. So one thing I want you guys to notice here is that this ester technically has an alpha transformation. I didn't draw it out like I didn't draw it downwards, right? Like I drew on the other ones. I drew it downwards to make it very obvious that it was a transformation. Like in the past, I've drawn it like this. And that makes it a little bit more obvious that the alpha carbon is transforming, but this is also an alpha transformation, especially considering that the starting material is 3 carbons, right? And this material here is 4 carbons. So there's clearly been a transformation that's been taken place here, right? Things have been changed. And so we could think about, okay, we could cut, so this is the alpha carbon, we can cut here and say that, okay, this came from these two pieces here. And we could try to think about how we could conjoin these two pieces. But remember, I already showed you guys what we could look for to understand what went on. So what I mean is, let's look at the fragment that came out of this reaction. So this is the alpha carbon. Then we added 2 carbons and an oxygen. We go back here. What was the fragment that was 2 carbons and an oxygen? Who had 2 carbons and an oxygen? The answer is the epoxide. The epoxide had 2 carbons and an oxygen. So this aldehyde probably came from an epoxide. Well, if epoxides give us alcohols, that must mean that we oxidize an alcohol, right? Because we have an aldehyde instead. So we can un-PCC this guy, and we can get an alcohol here. Now it's very obvious that we have an OOH, right? We have the CCO. Oh, sorry, OOH, I meant CCO is what I meant. It's very obvious we have a CCO here. And again, we can say, okay, this just came from an epoxide and an ester. So yes, you could have started with the acid, or we could have done the cut here, started with that, and said that this came from a carboxylic acid and alcohol. There's nothing wrong with that whatsoever. Actually, I'm going to modify something here. I'm going to make this 3 carbons long, and you'll see why I'm doing that. But keep in mind what the important part of this reaction is recognizing that it's an ester and it's transforming right on the alpha carbon. So undo those alpha carbon reactions first, and then get to the bare bone component of the acid and the alcohol. Fischer esterification. Right now, this acid, right, is 2 carbons long. This ketone is 3 carbons long. How do we get from here to here? How do we go from more carbon, or how do we subtract out a carbon? It's clearly the haloform reaction. So NaOH, H2O, X2, right? That is the haloform. That's what's going on there. Now, the reason why I turned this into 3 carbons is because we can also make the alcohol as well, because this is a 3 carbon unit and this is a 3 carbon unit. You just have to be a little, clever here, but we just have to get the alcohol. So we have to, transform this carbon's functionality over to here. The way that we do that, the way that we transfer functionality from vicinal carbons, if that will help you remember, vicinal carbons, that is by using an alkene. So this is going to take a bit of a second. So we have to do like a NaBH4. H2SO4 will work here. So H2SO4 in heat. Then we can do BH3, right, THF. That gives us the alcohol that we want. Okay, so it takes us about 3 steps. Not too bad, but you never know if she might ask you to make everything possible, right? You might be asked that. You might be asked to make everything possible. All carbon units, right? You have to make them. Cool. So this one, I really like this one because again, it forces you to look for a relationship, right, that you are aware of. Cool. All right. We can do a little bit of a simpler one actually right now, just if things are getting a little bit too fast. Let's do one that's a little more slow pace, and hopefully everyone can get this one so that you feel a little bit better if you haven't been doing well on the past syntheses. But again, here's what I'll say: if you haven't been doing well on how to answer these synthesis problems, hopefully you're taking notes and seeing how I do them, or you're seeing the patterns that I look out for. Because that's what synthesis really is. You look for a pattern and you just see it replicate over and over again. Okay, so don't feel too bad if these are difficult. I mean, they're meant to be difficult, right? Especially if these are the first. Some of you, it's like the first time you've done synthesis in like months, right? Maybe even in a year. So it's totally okay. So this problem here looks very difficult, but it's not too bad. Okay, this is just a very simple choosing of what kind of synthesis we use here, because you should notice 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. We added a carbon. So we're doing either Grignard or we're doing nitrile. Now, again, this intermediate here is either going to be a nitrile or it's going to be a Grignard, right? So the intermediate before is always going to be this bromide here. How do we add a bromine to that tertiary carbon? Very, very simple, right? That's just Br2HP. So the question just becomes, right, which synthesis do we want to do? Do you want to do nitrile or Grignard? And again, just run through the list, right? We go through substitution, hybridization, and then basicity, right? Substitution is probably where we're going to call the line because it's a tertiary carbon, right? This is a tertiary carbon here. So we're probably not going to want to do the nitrile. We're going to do the Grignard sum. Okay, so very, very simple, this one. And sometimes you get a simple one like this, right? And that's when everyone's happy because we got a simple one. All right. Cool. So I'm going to take a second to think about which one I want to ask now. Ask next. Just trying to think of things that I haven't covered yet that might be worth covering. Oh, I guess we can do another simple one, but it has like a little bit of an interesting twist to it, actually. I just remembered this one. Okay. So this one looks like a typo. It looks like there was like a misprint or something. But we do start from one fatty acid and end with the other. So this is sort of like a fatty acid elongation reaction if we had to do one. Again, do everything you have to do to figure this out. This one is going to require you to be a little more clever though, or maybe not clever, but you just have to look back at your reactions and notice that there's a very easy way to do this one. Cool. So what I would have done first, maybe hopefully most of you did, was you counted your carbons, right? And you notice that there is 2 more carbons here. So if we're adding 2 carbons, there's only really one way to do that. That's an epoxidation reaction, right? So we can un-Jones this to, because remember, epoxides make alcohol, they don't make acids. So we can un-Jones this to get back to the alcohol. And then we can think, okay, this was from an epoxide, right? That reacted with MgBr. Okay, so again, sorry if I'm going too fast, but let me show you. So we're going to cut this off. We're going to undo the Jones on this carbon here. So we're getting rid of this guy. And then we're cutting off the CCO fragment, right? We're cutting off this fragment here. And so again, what is that going to leave us with? It leaves us with an epoxide, and Grignards are what open epoxides, right? Not nitriles. So we're going to end up with this. And so the question just becomes, how do I go from this 4-carbon acid to this 4-carbon Grignard? Well, we know that Grignard comes from bromides. So the question then becomes, how do I turn this whole acid group into a bromide group? Now we know how to do derivative, right? So we know how to do derivative to amine, right? But now what we're asking is derivative to bromine. This one's a little more difficult, but you have to kind of remember, or maybe if I did this, right? If you ignored this carbonyl, right, would this become easier, right? Or if I thought about the carbonyl alcohol, which one do we think is easier to turn into the bromide? I think I gave it away with the first one. Maybe I shouldn't have done that. But essentially what I'm thinking of here is, well, I know a reaction that adds a bromide to an acid, right? That reaction is PBr3, for example. That makes the acyl halide. So PBr3 can transform alcohols into bromides, right? Well, here, all I need to get rid of to get to the actual bromide is just get rid of the carbonyl. Because if I get rid of the carbonyl, then it's just an alcohol reacting with PBr3 to make the bromide. So how do we get rid of the carbonyl, right? How do we get rid of the carbonyl from the carboxylic acid? There's really only one way to do this. It's lithium aluminum hydride. So lithium aluminum hydride will get rid of the carbonyl, right? And then we can just do PBr3 and we'll get here. So we haven't done very many reactions like this in synthesis quite yet. And I will actually, introduce, we should do a couple more, probably like 5 or 6 more of these. And I'll introduce more of these reductions, but this isn't, a way to make alcohol. So keep that in mind. Getting rid of that carbonyl, right? Lithium aluminum hydride will do that for you. Okay, so this one's a little bit of I would say it's a bit of a medium one, because maybe that first step might have stumped a couple of you. But hopefully now you can see my reasoning of how to figure it out, right? You kind of have to use your knowledge of, hey, we can turn this into, we can turn acyl acids into acyl bromides. So why don't we just turn an alcohol into a bromide the same way? Well, how do I get the alcohol? That's just a reduction of the carbonyl. Okay, cool. All right. So with that being said, let's go ahead. Let's try a new one or another one. Let's do yeah, so let's do this aldehyde 2. So this one probably looks very difficult, which is okay. It is a little difficult, I would say. It is a little difficult. But again, just here's what I would say is maybe try to think about where that amine could have came from. Okay. Now keep in mind, oh, you know what? Yeah, do the problem, and then I don't want to spoil anymore. So try this one on your own. This one's a pretty difficult one, I would agree. Okay, so the amine probably threw off a lot of you guys, and you probably thought that I was confusing some chapter 21 reaction with this. But you guys do know how to make amines in this class. You just have to go back to the one derivative or the two derivatives that have an amine, right? And think about, or to have a nitrogen, and think about how they make amines. So the amide and the nitrile. In both cases, the amide or the nitrile, if you react them with lithium aluminum hydride, they make amines. You'll notice that basically any derivative, right? A good way of seeing how the reaction works out is you're kind of just getting rid of the carbonyl, right? So for example, with the carboxylic acid, it's kind of just doing this and we get that answer, right? Actually, you know what? I don't want to give you that trick because that's not always going to work. But for the amide and the nitrile, it's essentially, getting rid of the carbonyl or getting rid of the pi bonds. Okay. In the practice guide where we do practice problems, I'll give a better idea of how to do the hydride reactions actually. But in terms of amines, the way we can make them is with lithium aluminum hydride. Now, here's the thing. I made this symmetrical on purpose because I didn't want you to worry about where we make the amine, right? But we were just going to, or where we put the carbonyl, right? Where the amide was originally at, but we can just put on either side. This side will work. Okay. And so once we get to this amide here, right, maybe now it'll be a little more easier to do this problem. But yeah, you guys can totally make amines. And maybe, right, again, this is another good segue into adding chapter 20 reactions to midterm 2, right? It's making you guys make an amine from an amide via lithium hydride, and then, doing other chapter 21 reactions. So now that we get here, again, we can just cut there and say, hey, this is what I get from that, right? And acyl halide of 3-carbon unit from, aldehyde 3-carbon unit. We're just going to do a Jones here. Carboxylic acid. And to get from here to here, it's just SOCl2. Okay. So amines are totally accessible. We can totally make them from amides. And one thing that might be now confusing to a couple of you is why, what am I doing differently from the Hoffman reaction? Because the Hoffman reaction might seem similar. So I'll give you guys 2 examples. If I do lithium aluminum hydride here, essentially all I'm doing is just getting rid of the carbonyl. So I have complete retention of the carbon skeleton, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. If I try to do Hoffman reaction here, well, first off, Hoffman's not even going to work. It's NR. Okay, because remember, what is the only substrate that Hoffman works on? Hoffman only works on primary amides. Okay, so it would only work on this one. Also keep in mind that when we do this reaction, we are going to lose a carbon. Okay, we are going to lose a carbon, right? Because we go 1, 2, 3 to 1, 2. Again, this whole group here, the whole acyl group is converted into an amine. Here, the only thing that's going on is this. So in this case, we're just getting rid of the carbonyl, right? So I guess you could say this is being replaced, I guess. This is being replaced with H, but this whole group here is being replaced with NH2. So if you wanted to make an amine that lost a carbon, you use Hoffman. If you're making an amine that keeps all its carbons, its skeleton is the same, right? Carbon skeleton is the same, then you want to use lithium aluminum hydride. Now, the hydride reaction actually gives us access to something else too. That's a little bit interesting. And for this one, I won't really do a synthesis. I will just kind of tell you. But let's say we do the acyl halide to the, let's say we do, let's do this one. Let's do this primary alcohol here. We'll turn it into a carboxylic acid. And then actually, I don't know why I keep doing it backwards. Let me take that away. Let's do it this way. That's facing upwards, which most of you are probably more comfortable with. Okay. So I just want to highlight a synthesis here, and then I'll kind of go the bare bones of it. But we can turn this into this. Let's actually do this one. Let's do NH like this. And then we could do this. And then we can do this. Now, if we were to look at this reaction from the beginning, essentially what I'm doing is this to this. Okay. Now, this reaction, actually, I can even, let's start from here just to make it even simpler, right? Now, this reaction looks really, really weird because if we were tracing it, it looks like we kind of switched the position of the carbonyl, like it was on the left and now it's on the right. And that's kind of what we can do with amines. With amines, right, we can completely switch the location of the carbonyl because, again, amines are really good substrates for acylation anyway with acyl chlorides. Doing this reaction or doing the synthesis in retrosynth is very simple because I think it helps make this idea more obvious. But seeing here, like we can see that this is the 3-carbon chain, right? This is not a 3-carbon chain; it's a 2-carbon chain. So you might get a little confused as to how to continue. I can actually see a slightly clever answer here. Oh, actually, no, I do not. It's not really that clever because it's really long. But if you were to match that 3 carbons, you might see it here. All I'm trying to get at this point is you want to notice that the carbonyl, like it kind of moved places. Seeing it in a forward way, it might be a little bit hard to see, but seeing it retrosynthetically, I think is very easy because retrosynthesis, all you need to notice is, again, this came from, right, an acyl halide and an amine, right? So like this. So it came from these 2 components. And then the hard part now is just figuring out, okay, how did I get this amine? Well, once again, right, if this is a 3-carbon unit and this is the 3-carbon unit here, right, how do we make amines that retain that carbon skeleton there, right? We make that from lithium aluminum hydride. So you might be thinking, well, what about this methyl here, right? That wasn't in the original skeleton. Well, bear with me here, because really what I'm saying is we're retaining this skeleton here. It's this 4-carbon skeleton that we retained. We made that by reduction of that amide. And then the question is, okay, how do I get from this amide? How do I get from this acid to this amide? Well, again, we have to use SOCl2 to make the acyl chloride, right? And then the acyl chloride is reacted with the amine of choice. So again, if I have a secondary amine, right, that's going to be from a primary amide. Sorry, secondary amide, that's from a primary amine like this. Okay. So this problem, okay, kind of banks on your idea of understanding retrosynthesis a little bit, or at least employing it a little bit, because I think doing it the forward way is a little bit difficult. It's a little bit difficult because you really have to stretch your mind to think about, oh, okay, if this 3-carbon chain is this one, it looks like we made it into an amine that we then acylated. But I think that's hard to think about. Just think about it retrosynthetically. I know this amide bond comes from acyl halide, or if we do it the way that we've been doing it before, it comes from some acyl derivative and amine. Well, what's the only way to make amides is with acyl chloride. So it came from these 2 components here, right? It came from these 2 components here. Well, how do I make the amine? Well, again, amines, there's only 2 ways to make them. It's Hofmann or it's lithium aluminum hydride. If I look here, 3 carbons, I think it's lithium aluminum hydride. So I undo the lithium aluminum hydride, which puts the carbonyl there. And again, I see that, okay, this basically was an acid to amide reaction here. Acid, acyl halide to amide. That's how I get my amide, reduce it, re-acylate it, and I get the new position of the carbonyl. Okay. This one, I imagine, might take 1 or 2 watch throughs because it's a bit of a, it's a bit of a lot of information. But that's one way. That's one way we can shove a bunch of reaction concepts into one single synthesis. Actually, this synthesis can get a little more complicated too, right? If you imagine that we go actually from the, if we go from the 3-carbon chain to the 2-carbon chain, okay? So this one can actually get a little more difficult because imagine if this was our endpoint here, okay? I don't imagine you'll ever get a problem this hard, but it is something worth considering, right? Because again, if we do the hardest problems now and you guys get exposure to it now, then on the exam, you'll be prepared for it when you see it, if you were to see it, okay? Again, if I do the retrosynthetic approach, which is what I like, and we know that this came from acyl halide, right? So again, some acyl derivative made this, probably the halide because it's an amide, and it came from this amine here. Once again, I have an acid derivative and an amine, but notice how if this is a 3-carbon chain this is now a 2-carbon chain, right? Now, the reason why I fixate on this carbon chain here is because when it's the same, we know it's a lithium aluminum hydride reduction. There's really no way to go from 3 to 1 carbon. That's how you know we don't have to focus on that carbon at all. Same thing here as well, right? 3 to 1, there's nothing that gets us 2 carbons off like that. But 3 to 2, especially when it's an amine, right? We know how to do that. 3 to 2, oh, actually, I got to change this. This has to be an H. So maybe this will make more sense now. 3 to 2, right? That is going to be Hofmann elimination or Hofmann rearrangement, especially if it's a primary amine. So really the smoking gun here should be the primary amine, but the 2-carbon loss or the 1-carbon loss also helps out as well. So X2, NaOH, H2O. This basically came from this primary amide here. How do we make this primary amide? Very, very simple, right? We know how to do that. Okay, cool. So hopefully I was not as confusing as I think I was. And if I was, please ask more questions, right? Ask questions in the comments. Let me know what I could have explained better. Maybe I'll even make a follow-up to make this a little bit better. But the point that I want to make here, right? The point that I want to make here is that amides, we can do very crazy things with them because of the reduction aspect there, right? They can get a little crazy with them. They can get a little bit weird with them, okay? And they make our lives slightly harder, just slightly harder, okay, for that fact. But what you just want to realize is if I have a 3-carbon chain that's retained in my synthesis and I sort of swap the carbonyl on the amide, I'm thinking lithium aluminum hydride into reacylation. Okay. If I start with some carbon chain and I lose a carbon somewhere and I make a primary amine, right? Or my retrosynthetic analysis gives me a primary amine, I'm thinking haloform. I'm thinking, sorry, or the Hofmann rearrangement, right? Because then I can go from 3 to 2, get that primary amine and reacylate to get that amide there. Now there is one more added level of complexity here. So I apologize. I know this is getting complex. I know this is not the greatest, but let's take this problem here, but say that we kept the 3-carbon chain. So let's say that we kept the 3-carbon chain. Okay. And actually, maybe what we want to do here is a 4-carbon chain. Let me think. What do I want to do here? No, I think 3-carbon chain is fine. Okay. Let's say we kept the 3-carbon chain. They might be thinking, but what's the complexity here? Wouldn't it just be this one here? Yeah, you could do this reaction here on this one, right? It will work. No, not going to argue on that. That can totally work. Okay. The only thing that I want you to realize is that there's an alternative pathway here. Okay. So let's actually go to the amide. So there's going to be 2 steps here, right? One's going to be the acylation, or sorry, the SOCl2, and the other one's going to be the introduction of the amine. Okay, so we'll get here. But I want you guys to realize that there is something else we could use here to get what we want. We could also turn this into a nitrile. And then the nitrile we could reduce with lithium aluminum hydride. Now you might be thinking, well, doesn't that add a step? And it does. It does add a step, right? Because we could have just done lithium aluminum hydride straight to here. That works too. But I just want to prime you guys for the last part of this synthesis guide where we consider the importance of the nitrile. Okay, so don't forget the nitrile also exists. Okay, the nitrile also exists here. So this is not really, I don't want to say this is an added level of complexity, but this is like an alternative that you could use, although technically the pathway to here is a little bit better. Right, but I'll remind you guys, primary amide, SOCl2. Remember, it has to be primary, otherwise it's not going to work. Okay, and there you have it. Okay. So last part of this video, probably 30 more minutes, guys, just 30 more minutes. Okay, I apologize. I know this is nearing a very long length, but I imagine most of you will probably only watch the end part of this anyways. Let's consider how nitriles might be useful. Okay, and so now that I've said nitriles, it's a good thing because now you'll be primed to think about everything we're going to do here. Okay, so let's say we have this amide and this ketone. Okay, so go ahead and try this. What I will tell you, the best way to approach this problem is think about what makes a ketone. And I think it will become very obvious what you need to do. Just think about what makes the ketone. Okay, cool. So if you paused and tried, great. And you thought about what makes the ketone, right? Remember, if we go back here to the reaction maps, there is only a handful of things that make ketones, right? Wayne-Reb could work, but we're not going to consider it because, we're just doing, we don't have to. But if we think, right, esters cannot make ketones. Amides cannot make ketones, but nitriles can. Nitriles can make ketones. And halides and anhydrides can make ketones. So the fact that we're ending with the ketone is actually very, very valuable to you guys because you know exactly where this came from. It either came from a nitrile or it came from like an acyl halide. Acyl halide is probably the better bet here. Between acyl halide and anhydride, I would on paper go with acyl halide. Okay, you don't have to always go with the anhydride, but the point is that we have one of these two options. Now, to know which one is better or which one might be better is just look at the starting material, right? This is a primary amide, and which one can we turn primary amides into? Can we turn them into acyl halides easily, or can we turn them into nitriles easily? Because this is a primary amide, we can turn this into a nitrile a lot easier, and therefore we can do the Grignard a lot easier with the nitrile. And so this is one accepted pathway for this. You could do the hydrolysis. So a couple of people did do this. They did a hydrolysis into SOCl2, right? And then they turned this into this with the Gilman reagent, which I guess you could do that. But the cleverness of this problem is that the amide is primary. The only time I would want to do the hydrolysis is if the amide were not primary, right? Because then you have to go through this SOCl2 pathway or the acyl halide. If it's this here to the ketone, you're kind of forced. You really have no choice to make the ketone here. Or sorry, to make the ketone from the acyl halide here. So you would hydrolyze, turn this into an acyl halide or anhydride, up to you, and then do Gilman, right? R2CuLi. Okay, where R is this group here, the ethyl group. So you're a little bit forced to in this case. But if you see a primary amine, by all means, just immediately jump the gun on that. Okay. You really want to prime yourself to the nitrile because for midterm 2 as well, there's going to be more nitrile reactions or reactions where we can add nitriles to things and we can turn those nitriles into what? You guessed it, into ketones. So you really do want to prime yourself to the idea that you have that available to you. Okay. I'm trying to think of if there's anything else. I think that's mainly what I want to talk about. I think I got everything that I wanted to talk about for this class, for midterm 1 synth guide. So as always, when it comes to synth guide is never meant at all to be a exhaustive, an exhaustive gallery of every single transformation that's allowed, right? Like this is not covering everything that you're going to see and only things you're going to see. It's just meant to prime your brain to think about what is allowed and what isn't, what to think about and what not to think about. Okay. I guess there's one more reaction that I could do just to prime you to the idea of things. So I will do that. Oh, you know what? This would be, let's do it from here. Okay. So this is one more reaction we could do. Okay, but again, really want to emphasize this. In no way, shape, or form is any synth guide that I make supposed to be completely exhaustive of every single thing you could ever do. These guides are just made so that you can think. You're allowed to think about what transformations you can do, what you can't do, and what to look for in anything that you do. Okay, I don't want I don't want there to be a, like in the past, there has been a sort of a bit of a sentiment with previous classes that, oh, your synth guide only covered this, this, and this, but on the exam there was this, so I didn't know what to do. It's like, well, one, that makes me feel terrible because I feel like I should have guessed it. But two, no way, shape, or form is any guide meant to be completely exhaustive. It's only meant to start to prime your brain as to what's allowed and what isn't. Okay. No shade to any other class, just a little thought. Cool. So this problem here is a very, very interesting problem. Definitely try it. I think that the way I've written it, it's really makes you want to do something. So I want you guys to do that something and see where you get. So go ahead and try it. Cool. So what I want you guys to notice in this problem is, again, there's an ester, and on the ester, there is an alpha transformation. So I think the very first thing a couple of you probably tried doing was, how do I get, some kind of ester group there? Okay. Now, in general, I would not advise this, right? For any alpha transformation, especially if it's an alpha ester transformation. But I think it might help you guys to cut these bonds first, actually. Okay. Because if you do that, you get a diacid here. And this diacid might help you think about what you need to do to continue. Because I think that if you try to think about ester reactions, again, in terms of ester enolates, remember that ester enolates add electrophiles. They add electrophiles. So if we did have an ester enolate here, right, the only electrophile, oh, you know what? Actually, there is a way to use the ester enolate here. Okay, so I guess there's two viable pathways now that I think about it. So this is a really good problem, actually, because there's two viable pathways. So let's do the way that most of you probably did it, and then I'll show you my way, the way that I was thinking about when I was doing this. So you can notice that there's an alpha transformation and cut this guy off, because clearly the original chain is these three carbons. It's these three carbons. You can actually maybe even start to do a little bit of a forward here, because you kind of notice what you need to do is turn this into this with Jones, and then turn this into this, right? Fischer esterification, right? And then we just do the, we make the alpha enolate. I would use LDA because that means you can LDA basically lets you like isolate almost entirely of the ester enolate. But once we get to here, right, and we think about what can we react with, right? Again, think about what this group would here, what kind of electrophile could have been born, right, or could have born this group here, right? And if we look, right, it's an alpha transformation where there's immediately a carbonyl, right? So it's like a CO with a carbonyl. If we go back to here, right, which one gave us a carbonyl, right, or a CO bond, right off the alpha carbon? So which one gave it? Blue, light blue, purple, red, or I guess this could have been some color, but it doesn't really matter. Which one could have been? So it's going to be this one down here, right? Oh, sorry, not this one. Oh, actually, I guess it could have been this one, but the one that I wanted to think about. Oh, yeah. So it's going to have to be this one here. It's going to have to be this one here. Oh, so then it's okay. I don't know why I thought it was this one for a second. Because this one actually makes things complicated. So it actually cannot be this one, but it's going to be this red one here. But remember that it makes a CO single bond, not a CO double bond, unfortunately. So what we're going to have to think here then is that if we added a CO that can transform into an ester, we want to use a formaldehyde, okay? And the reason for that is because, oh, sorry, I just wrote the same thing. When we form this, we want this group here, this OH, because we can then oxidize that OH into an acid, and then we can turn the acid into the ester, right? We can just do a Fischer esterification. So we can just add in the same reagents from before. So this one, a little bit interesting, that we can actually use the alpha enolate here. That actually works. You could do that. Add the formaldehyde, and then oxidize, and then do the Fischer esterification. The other pathway that I see here is if you're clever enough to notice that both of these esters could have been born from a diacid. Because if we have a diacid here, a carboxylic acid with alpha transformation means that it came through HVZ. And so now you just have to think about what can I transplant that, or what can I substitute that Br for that can turn into acids? You could have turned it into a nitrile and hydrolyzed on that. So this is a really good problem, I think, because there's two different ways to do it. I guess it's depending on which one you think of first. I think technically speaking, this one is actually the absolute best way, even though it's a little bit longer because HVZ kind of sucks. I know that this one, it would just, so, okay, so let's do it this way. So it would be 1 to the step, then 2, then 3. So this one's a bit shorter. It's 3 steps. So maybe you might want to give up a bunch of days just so you do only a 3-step synthesis, right? This one here is what, 1, 2, 3, 4, 5, 6 steps. So it's about double. It's about double the number of steps. Okay, which is not always the greatest thing to have, but I would imagine that maybe doubling this, oh, I might make it equal. So I would say these either doing the HVZ pathway, right? So then this would go over to here, right? So then 1, 2, 3, 4, sorry, it's 4 steps. 1, 2, 3, 4 steps. Oh, adding 2 steps wouldn't be too bad, right? 1, 2, 3, 4, 5, 6. Adding 2 steps isn't too bad. I guess it's a matter of picking your poison. Do you want to wait like a million days for HVZ, or do you want to add 2 steps that could effectively reduce your yield by quite a bit? Cool. So I just wanted to show that because I wanted to get a little bit more HVZ action. Just keep in mind, right? HVZ is nucleophiles showing up on that BR position. So maybe instead what I could have done was added an amine here. 20 more pre-med points if anyone can get this one. Who can get this one? Which amino acid is this one? 20 pre-med points. That is alanine. Okay, so if you got it, you can, I don't know, store your points in the bank. I don't know. Anyways, cool. So I'm going to call it there. I think this is about 2.5-ish. Hopefully it's not too long. I'll try to do some chapters or something, or put some like timestamps so you know what, where you can look for. But I highly recommend that if you're at the very least not even going to watch the first part, at least watch the back end, like the last hour and a half of this, because that's really the synthetic practice of what you really need, right? Cool. All right. Any questions? Please let me know. If there's any mistakes, please let me know. If there's enough of them, I'll try to remake this and re-upload this. Although this is the Tuesday before your exam, so probably not very likely that I will be making a new one for you guys, maybe for future classes. Cool. All right. Have a good one, guys. See ya.